All right, so good morning, everybody. My name is Oliver Dragicevic. I work at the Faculty of Mathematics and Physics at the University of Ljubljana. And I'm speaking here as a member and on behalf of the organizing committee of the conference Harmonic Analysis Days in Ljubljana. It is my great pleasure and my privilege to welcome all the participants of the conference here, all our esteemed speakers, and above all, Professor Alexander Wolberg, to whom this conference is dedicated, more precisely to whose 70th birthday. We have ahead of us a couple of exciting mathematical days, very exciting talks, and hopefully very exciting informal conversations. Now, this would not have been possible without support of several Slovenian mathematical and not just mathematical institutions, by which I mean the Academy of Sciences, Slovenian Academy of Sciences and Arts. We are now hosted in the Academy's building in this wonderful hall. Other supporting organizations are Faculty of Mathematics and Physics and Institute of Mathematics, Physics and Mechanics. I'm very glad to welcome here representatives of all three institutions. I'm going to call them one by one, and again with our gratitude on behalf of the organizers. So first, let me greet here our colleague mathematician, member of the Academy, actually the acting Secretary General of the Academy, Professor Franz Forstnerich, who will say a couple of words on behalf of the Academy. Please, thank you.
Thank you very much, Oliver. Honored guests, dear colleagues and friends, I have a very pleasant duty and privilege to welcome you in Ljubljana on behalf of one of the institutions which is hosting this event where we are sitting right now. This is the Slovenian Academy of Sciences and Arts. So in the next few days we shall be celebrating an anniversary of Professor Alexander Wolberg, Sasha to his friends. Professor Wolberg originally came from the very famous school, Havin School of Analysis, of Mathematical Analysis in St. Petersburg. And he has been one of the leaders of the field of harmonic analysis and also several related fields over several decades. More on his career and his work is going to be said by Professor Nikolsky shortly. I wish to add that close ties between this eminent group of mathematical analysts in the world, coming from the school and others, from the St. Petersburg school and of course many others, was forged almost 2.5 decades ago by Oliver Dragicevic, who obtained his PhD in East Lansing as a student of Professor Wolberg, and they have collaborated since. I wish to use this opportunity to wish Professor Wolberg all the best, both in a professional career and in his personal life. And I'm very much looking forward to an interesting conference. Thank you so much.
Thank you. Now I'd like to introduce the Dean of the Faculty of Mathematics and Physics of the University of Ljubljana, our colleague, Professor Emil Žagar, please.
Thank you very much, Oliver. So, dear guests, dear colleagues, warm welcome on behalf of the Faculty of Mathematics and Physics, University of Ljubljana. We are delighted and honored to guest such a prestigious conference with so many extraordinary invited speakers. I'm not an expert in harmonic analysis, but Alexei introduced the scope of the conference and also some invited speakers. And it is clearly seen that it's an important international mathematical meeting. So congratulations to the local organizers for getting so many people here in Ljubljana. Of course, a special welcome goes to Professor Wolberg on the occasion of his 70th birthday. So happy birthday and all the best, Professor Wolberg. I'm confident that this meeting will be full of new mathematical ideas, discussions, opportunities for new collaborations. So enjoy the conference and your time here in the city of Ljubljana. Thank you very much.
Thank you. At this point, I'm happy to introduce the director of the Institute of Mathematics, Physics and Mechanics of Slovenia, our colleague, Professor Peter Šumaru, please.
So thank you, Oliver. It's an honor to say a few words here on behalf of the Institute of Mathematics, Physics and Mechanics. The Institute brings together all researchers in Slovenia. Please keep in mind this is a very small country, small population. With this in mind, let me say something. My personal opinion is that for a country of this size, the quality of research in mathematics in Slovenia is, let me say, at a very reasonable level. So this might be a biased statement, but we are mathematicians, so let me try to give a proof. One possible proof, I look at this conference, I look at quite a few very highly distinguished mathematicians in the audience, and then to me it is obvious it would be impossible to attract such a prominent group of mathematicians to Slovenia without having a certain quality on the side of the hosts. End of the proof. After the proof, a remark, personal remark concerning the hosts. I'm speaking about the organizers. From my point of view, they are very young. Corollary to all this, when I think of the future of Slovenian mathematical school, I can be very optimistic. I have all the reasons to be very optimistic. And this conference itself, with its quality, makes me feel comfortable when I think of the future of mathematical development in Slovenia. And therefore, I would like to thank you all for coming to Ljubljana, making this a really great, important event. I would like to thank the organizers for all your hard work, for attracting such good people, and a great pleasure, Professor Wolberg, to congratulate you on your birthday with all the best wishes. Thank you very much.
Thank you very much. As the last speaker in this opening session, I'm very happy to welcome to the podium Professor Wolberg's graduate advisor, who is here with us. That's Professor Nikolai Nikolsky, who will say a couple of words about Sasha. Professor Nikolsky, please.
Thank you very much. I'm very glad and proud to open this conference, and I think that this privilege is given by the organizer to me because I maybe, but not maybe, but surely have the most long-lasting friendship and mathematical relation with Sasha. It's about 50 years, a little bit more, and so I will try to trace very rapidly the Sasha's way in mathematics and in his, maybe with some point on his youngest years in the beginning in St. Petersburg, Leningrad at the time. But how to animate this thing? What is it? What is it? Mm-hmm. Full screen. Okay, yeah, and here this one,
so.
yeah.
Let's try.
And
Good.
okay, so it is of course more or less impossible to survey what Sasha did in mathematics because of the obvious reason, just numerically. He has more than 200 important papers with maybe no omission. There is no empty or still easy text in mathematics, and 2 influential research monographs, and such. Some other figures are also impressive. In particular, he has 90 collaborators in the list, and his Erdős number is equal to 2, which is also rather rare now, because, say, the medium of the Fields medalist in Erdős number is 3, not 2. So it is, and but however, I can distinguish 3 circles of interest of Sasha, which are here presented in the beginning. It was complex analysis, more or less pure. Then it developed to harmonic analysis in more general and more important setting. Now or from some time, of course, it is Bellman time to apply this method everywhere for obtaining the optimal results. So let me say a few words about each of these 3 circles. So this is the usually the uniqueness and completeness problem in complex approximations, but also the analysis of the harmonic measure on some thin subsets of the complex plane, and in Rn, of course. And so I have some favorite in every circle, and this one is this uniqueness theorem, which generalize and make the last point in the long history of this theorem. I mean that you have not holomorphic function for which the result is just the Jensen inequality, which implies that the logarithm of the modulus of Hardy H1 function is summable, but Sasha considered the just summable function on the circle, whose anti-analytic part is sufficiently smooth. I mean smooth, in non-quasi analytic sense, as it is written here. And so he proved that the logarithm of modulus is still summable. it is very strong result, and it is very sharp, of course, because if the series converges, so this is the non-quasi-analytic case, and there is the functions of this class with very small support, so is no uniqueness, no summability, of course, and also the technique used the so-called Seva-Denkin asymptotically holomorphic functions, which was very new at this moment when Sasha applied it, and as said, the Russian joke on this thing, the Jensen, Levinson, Cartwright, Berling, who occupied by this problem, go on holidays. I don't know how to say отдыхают. Jensen, Berling, Levinson, Cartwright отдыхают. Okay, so it is for the first one. There is much more, of course, the papers related to this first circle. The second one is the Calderon-Zygmunt operators on Rn or even on the manifold and the metric measure spaces, and the matrix AP weights, and the new technique of averaging the dyadic lattices. Of course, Sasha liked very much to work in some beautiful companies that I will list it after. This is so many papers and many achievements. It is shared with his collaborator. But this is exactly him who is presented in every these important papers and theorems. Here, my favorite is the celebrated TB theorem without doubling condition. So you have the Calderon-Zygmunt operator, which is defined by this integration with the kernel, satisfying this condition. And so the theorem says that this operator is bounded if and only if it is weakly bounded, which is the last. I don't know how to push this pointer. So
I'd like to ask you to stand here.
Oh, yeah.
Otherwise,
Oh, yeah.
it is recorded, otherwise we do not hear.
Oh yeah. Sorry. So it is the weak boundedness. This is the last line in the screen, and so the test function b1, b2 can be chosen in your. This is your choice. The only is it weakly not attractive, but how it's accretive, yeah, weakly accretive with this inequality of integration over the cubes. Q is an arbitrary cube, and this theorem was very appreciated by the community. And for the proof, there was used the rather new or just new technique of the averaging over the different dyadic lattices to give. So it was some step in harmonic analysis which I liked very much. And the third one is the Bellman function. Maybe it is also almost 20 years when it appears, even more, 25. Yeah, but however, it's still the modern tool in harmonic analysis. From 5 principal investors or actors of the Bellman function technique, 3 is here, and so it's not me who will present this technique, so ask the creators. And so many applications up to now, it's still, the list still grows sufficiently fast, so this is some subject which I listed here, as the two-weighted inequalities, and so the solvent of the reproducing kernel test. What is it? It says that if an operator on the space with reproducing kernel is bounded on the kernel, so it's bounded in general. It's not true for the embedding, for the Carlson embedding of the model space k theta to L2 of mu, in particular, which is discovered with these techniques, and so on. Okay? So now I'd like to say some words about two monographs. So I'm sorry, I had some problem with the computer, so there is not listed here, but is the monograph of American Math Society on Calderon-Zygmunt operators on metric measure spaces. And the second one is with Vasily Vasyunin, who is here, Bellman function in harmonic analysis. You know, of course, the boss, maybe more than me. The monographs are very influential, of course. And so now I will speak a little bit on the Sasha way in the beginning, his youth years and his growth. So I took his personality and his acquaintance after a course in functional analysis in Leningrad, St. Petersburg University, when in the break between 2 hours of the course, so some young guy like here approaching, saying that I solved one of your problems which you asked on the preceding course. This was my method to select some good students, asking at the end of every course some list of 2-3 problems to solve, not for free, who can do 2 or 3 proofs, can get the upper note in the coming exams without being presented on this example, and Sasha was one of them. And the problem was something like, say, you have some system, some sequence of functions on the 0, 1, under what condition you can, this is the restriction of orthonormal basis on the interval 0 to 2. For instance, it seems that this is just this one, what I asked this time. And then the Sasha's way go in the St. Petersburg analysis seminar, which was mentioned already here, founded by Victor Havin in the 1960. I was in the third year of the university when the seminar started, and I participated from the beginning. We was 4 people in the very vast great room, and so it continued. It continued in the permanent during all Soviet years, at least it continued until now, of course. And so when Sasha came in the seminar room was already many people, not only the how to say, the old generation, as Havin himself, my friend Vinogradov and me, but also all these younger people, as Sevadenkin, Vasyunin, Alexandrov, Khrushchev, Shirokov, Treil, Makarov, Yoriki. And then Sasha arrived just here under the first wave, and the second one, and then was Boris Solomek, Malinnikova, Peller, Smirnov, Lagunov, and Nazarov. You can imagine what means a little asterisk there. What is the answer? because some people are marked by authority. This is the selling price winners in the different years, of course. So you can imagine when around the same table in the room like this, there is all these people with all their capacity to make mathematics. That I mean that for the seminar organizers like Harin and me, there was a really problem to choose the next speaker, because every week there was some new theorem or something. You know all these names, of course. It was absolutely exciting meeting every week, which last about 2, 3, sometimes even more hours, and it was very, very productive. Okay, and so some pictures with Sasha working at the table, with some collaborators there, with Vasilin and Sarah Azar trio, and me with Sasha Reznikov, and in Bordeaux during the conference. And so happy birthday, Sasha, and continue to make your beautiful mathematics. Thank you very much.
Thank you very much, Professor Nikolsky. Now we are going to take a 10-minute break. We resume at 10:20 with the scientific part. And in between, I would like to urge you, if you have not signed up yet for the lunches, now it's the time to do that, correct? So thank you, and see you in 10 minutes.
For questions?
For the questions at the end.
Yes.
I will fetch it, okay. I fetch a portable microphone, which will then be given to people who are answering the question, because answering the question is also heard. Okay.
It's okay because if I do it wrong, because no one will get hurt. So it's much pressure on you.
A moment. So we are ready to continue with the scientific part. Before we do so, a few very short technical remarks. First of all, if you have not yet registered or paid for the conference dinner and you are supposed to, please address Mr. Miloš Puja over there. And this is it. Now, regarding lunches, if you have not signed up yet, please put your name here. The sheets of paper will circulate. And finally, if you speak, please speak close to the microphone because the talks are being streamed and for technical reasons this is desirable. So now I'm off and the scientific session will be chaired by Professor Guy David, to whom I thank for this.
Okay, don't thank me too fast. Okay, so it's my pleasure to introduce Stephanie Peter-Michel, and her title is the Matrix A2 Conjecture, and she's from Würzburg. Please.
Thank you very much, Guy. Guy, can you hear me? So first, I would like to thank the organizers for this wonderful meeting, and in particular, my long-term friend and colleague, Oliver, who is so talented at mathematics and at organizing meetings. Thank you, Oliver. So I will talk about the matrix A2 conjecture, but given that this is a birthday conference, it will be an overview talk and somewhat historic. So please don't hesitate to ask any details in the end, because there won't be very many in this lecture. So let me start. So I'm starting with a disclaimer that luckily Nikolai already did for me. So here are two cakes. One of them is mine, the other one is Sasha's. So the one of Sasha, the weights, which is what I'm going to talk about in this lecture, is in dark blue in comparison to all of his other mathematical work, and for me it's more or less the opposite. So it's a little bit unflattering for me, except that Sasha is 10 people, you know, so it's not so bad. And after all, only one of us has a birthday today. So happy birthday, Sasha. So let me start with the lecture now. So let's first remember an object we are all very well acquainted with, the Hilbert transform, either on the real line or on the circle, which is a singular integral operator with convolution by 1 over x on the real line, and with a convolution by the 2 pi periodization of the function 1 over x on the circle, which also is known as the cotangent function. So we all know that the Hilbert transform is the magical object that gives us access to analytic conjugate functions, starting with the boundary values, let's say, on the boundary of the unit disk. So this is the central Calderon-Sigmund operator, the central singular integral, both in complex and in real analysis. So there are other ways to describe the Hilbert transform. The very standard one is by means of a Fourier multiplier that probably everybody is also well acquainted with, where we first take the Fourier transform, then decide whether the frequencies are positive or negative, and depending on that, multiply by plus or minus I to obtain the Fourier transform of the Hilbert transform of f. So, and then inversing the the Fourier transform will give us the Hilbert transform applied to f. So the Fourier system is a very natural system for working with the Hilbert transform, but for the kinds of problems that we are doing, it's not. For the very same reason why wavelets have certain applications outside of harmonic analysis that the Fourier system doesn't. So if you need to distinguish finesses that are local, wavelet systems are better. But the Fourier system is impressive because did you know that a electromechanic Hilbert transform sits in antennas? So if you have AM/FM radio, there is usually a carrier wave which is easy to transmit, and then an overlaying wave that's really your music. And the Hilbert transform is sitting inside the antenna and filters out the high frequencies, and with this split you will be able to hear your music. So this is really true. So since it's such a simple object of plus or minus 1 multiplication, this can be done. So there is a formal writing about what it means to be a frequency filter. So if you formally multiply two exponentials and one exponential in magnitude is much larger than the other, that's going to be the only one that the Hilbert transform sees, because this n in this case will determine the sign of n plus m. So it's really that simple. And interestingly, this idea enters into our work as well. So then I promised some matrix weights. So now the question is, what do you even measure with matrix weights? And you are measuring the, no, this is just scalar weights, I'm sorry, I'm ahead. So this is the scalar weights. So what is done? So the Hilbert transform as a singular integral is still computed with respect to Lebesgue measure. And then the resulting norm estimate in L2 should be computed with this perturbation of the weight. And the question is, when do you get bounds still L2 estimates? What are the conditions on the weights? It's been known for a long time by Hunt, Markenhaupt, and Wieden that this is such an estimate holds independent of f if the so-called A2 characteristic is satisfied. So the way to read this is to know that the product of W and W inverse pointwise is equal to 1. We all know that. And now you delocalize this by taking averages over W and W inverse. This product is always going to be greater than or equal to 1. But for certain functions W, it can become infinite, and we ask that it doesn't. So here it is, by Jensen's inequality, this characteristic is always greater than or equal to 1. So one of my first quite important theorems was to give the exact growth with respect to this A2 characteristic. And for the Hilbert transform, this exact growth was 1. Again, it was known that it's bounded for a long time. Over the years, there were certain improvements, and then 1 is optimal. I'll give the historic perspective on all this. Now we're ready with the matrix condition. So if your weight is now a matrix, it means that it is a matrix dependent on x. And it also means that it is, let's say, positive semi-definite symmetric matrix for all x, or almost all x. And we are going to measure the action of the Hilbert transform in the most simple way we can imagine. So we have a vector function f1 through fn. We will apply the Hilbert transform component-wise. And then we will measure its L2 norm with this perturbation of this matrix weight, where on the left-hand side I forgot to mention dependence on x, so it of course depends on x. So what is different from the scalar case? You'll have with matrices a lot more opportunities to mess up your situation. So scalars, positive scalars, they will basically give more weight to some intervals than to others. But with matrices, you also have the nature of rotations and different eigenvalues. So this is an entirely different problem. So the reason why it's more difficult, there's not only a stretching of certain actions, there's also a rotation. So your actions of the Hilbert transform on your different components of your vector will also be, the order can be changed, for example, or can be rotated. So it was an important, very notable result. Still one of my most favorite papers from the 90s, from Trail and Wohlberg. They have shown that this Hunt, Markenhaupt, Wieden condition is also the correct one for matrix weights. And along the way, they have opened a whole array of new techniques. So they have shown that the scalar A2 condition can be rewritten with matrices in such a way as here on the slide. So now, given that we have non-commutativity, we need to be really careful the order in which we write the operators. So this splitting in square roots is a very common theme. One can also show again that the A2 characteristic for the matrix weights is always greater than or equal to 1. So on the right it says if we are estimating something with a 3/2 power, that is worse than if we're estimating something with a 1 power. So this is true in the scalar case and in the matrix case. So the conjecture was that it's linear as well. I really don't know why now anymore, but we all believed it. So we thought there should be a linear estimate. The methods in weights developed very fast. Very strong people came into weights aside from our group. And eventually we tried again when we believed that things should be ready, and they really weren't. So at one point we published a paper that showed that there was a 3/2 bound, which was a slight improvement over another estimate that had an additional logarithm. So the joke was we forgot to drop 1/2 power, we only dropped the logarithm. But as it turns out, from 2024 we dropped as much as we could. So this 3/2 can indeed not be improved due to a counterexample that we constructed in the course of 2023 and 2024. So I'll briefly give one origin of this matrix-weighted problem. There are many origins where there are people in the audience much better suited to talk about than myself, but this here is one of them. So we should think of a stationary sequence of vectors to be a system that is modeled after the basis c to the n in L2. So if you dualize c to the n with c to the m, it's the same as dualizing c to the n minus m against 1. So when you have the same property, you call this a stationary sequence. When you have this in several variables, you will call this a multivariate stationary sequence. It is also known that c to the n captures everything. So you can just go ahead and change your measure and think about c to the n, and you'll capture the entire situation. Now, if you have a multivariate stationary sequence of z1 through cn with the same conditions, then your spectral measure will become a matrix weight. And the future are when the spans are all positive. The past is when the spans are all negative. And so as such, the norm of the Hilbert transform in a matrix-weighted case gives you information about the angle between the space of the past and the space of the future by simple use of trigonometry. So here you see if the angle is small, then non-surprisingly, the x, which is the difference of a vector from the future and the past, can be much smaller than the vectors u and v themselves, and if the angle is large, it cannot. So there are applications for this in so-called mixing of processes that I'm not going to get into. So this is one origin, and there are many to consider the Hilbert transform with matrix weight. So now I want to go back a little bit, the development of the sharp-weighted estimates. And it's hard for me to give a real historic perspective. I'm going to start the part that I sort of witnessed, at least as a viewer. There are other aspects of weights that Nikolai hinted at that I'm not going to talk about. But the sharp-weighted estimates, what led us to get our first estimates and what led us to the development of the sharp estimate for the matrix weights. So in my view, really this paper on matrix weights, this wavelets and the angle between past and future set a new tone. So for me, this was, of course, solving a very important conjecture, but it also had methods, these wavelet methods, that gives you better information locally. And also this idea to pass from dyadic to continuous is already in this paper, in my opinion. Then there are other papers by Nazarov, Trail, Wohlberg, the non-homogeneous T of 1 theorem, already mentioned by Nikolai earlier, by shaking grids, so by using different dyadic grids. And then there was also the two-way problem for Haar multipliers by Nazarov, Trail, Wohlberg that extensively developed embedding theorems and the Bellman function. But not to forget, there was always a parallel school of Perez and Lerner obtaining and others obtaining excellent estimates with predecessors of what we now call sparse domination. Now, what's better than this picture? So 1995, maybe 92, I don't know. So it's really from this time of those theorems and just one of my favorite. Aren't they cute? So, all right, so the first sharp estimates from our line of work were, for example, a result by Hukovic, Trail, and Wohlberg for the dyadic square function, a linear bound. Then a student of Pfefferman and later Koenig, Janine Witwer in Chicago, was self-training in this Bellman technique in the matrix weights case of Trail Wohlberg and the two-weight theorem of Nazarov Trail Wohlberg, and managed to filter out enough information and add some elements to get an estimate for the so-called martingale multiplier, where you take a Haar wavelet and pointwise multiply by a sine toss. Then Sasha and I were lucky to solve a very important weighted estimate for the Berling Alfors operator, which is the operator that convolves by 1 over pi z squared in the complex plane. So it is a big brother of the Hilbert transform in the complex world. This was, I want to say, relatively easy. I mean, we needed a new idea, but it gave a wonderful estimate, and it had wonderful applications. So we were fortunate to work on this together and solve this problem in 2000. Then my solution for the Hilbert transform is a little later, something like 2002 or 2003. And then the first really optimal large-scale bounds that didn't use the Bellman technique came out around 2010 or later. So I want to talk about what kind of methods were developed in our group and in other groups that came after us, or which methods did we use from people before us. So there are a few tools that I want to briefly illuminate. One of them are the dyadic model tools. So where do they come from? What are they? The Bellman functions, then the averaging that's been said, and the so-called sparse domination. So what do we mean by dyadic models? So the simplest way to explain them are through the use of dyadic intervals. So here you see a picture of the dyadic intervals on the real line, where they attach at the point 0 and cover the real line with many different sizes of intervals. And on this system of intervals, you can put wavelets, and in our case, some very simple wavelets of just step functions. And these step functions give us an orthonormal basis in L2. Then the dyadic operators that were used already before was the martingale multiplier. So this was understood as a model for the Hilbert transform already in much earlier work from the 80s. I would say by Bourgain and by Burkholder at the latest. There may have been earlier references, but these are the ones from the early 80s that come to mind in Banach space theory. So it was already understood this is a great model for the Hilbert transform. So what it does, it takes a Haar function and it then either leaves it as is or it swaps the sign. Then my operator was, by the idea of Sasha, to find a better model for the Hilbert transform, something that's closer. So what was closer was something that was a little bit more antisymmetric. And in order to accomplish this, you need to grab different coefficients that correspond to different intervals. So now the half function gets mapped to a combination of two smaller half functions as such as in the picture. The probabilistic aspect is gone, but in replacement there is something else going on. You would think, okay, well, this is an operator just as simple as the martingale multiplier, but it's not. It's actually quite a complicated operator. And the pictures here say a little bit why. So if you look at the flow of the dyadic martingale of F and T sigma F on the left-hand side, you will see that if your F moves horizontally, then your T sigma F moves within the butterfly that is drawn. So either it goes in the same direction up or it goes down, but it moves at the same time. And then you will have your next move. Your next move is again F moves horizontal and T sigma F moves either in the same direction or in the opposing direction. So this is the flow of the F versus T sigma F of the development of the martingale. Now the H shift is really different. So your F moves and your H shift doesn't know what to do because there is no next step, there is no previous step to look at. So the H shift has to wait until F moves again. And only after F moves again will now the shift of F think about what was the previous move. So now I know what to do. Okay, so this is called memory. So you have not a situation where you start over, you have a situation with memory. So these are the dyadic methods, and other dyadic methods is the famous Bellman technique. So this is a sort of an overwhelming slide, and it's just for visual pleasure. So in the center in the box is the dyadic Carlson embedding theorem. So you have a packing condition of measures in the dyadic upper half plane on the left. And then on the right-hand side, you have the conclusion, which is the L2 embedding of functions and their dyadic extensions. So with the famous constant 4. And normally there are many ways how to prove this theorem. You can use maximal functions, you can use classical tests on dyadic intervals for boundedness, and Bellman function is just one of the techniques. And if you're going to use Bellman functions, what does it mean? It means that you are looking at a function more or less guessed from somewhere. The function is on top with 3 different variables. So the variable m will represent the sequence of alphas. The capital F will represent the L2 norm of f. The little f will represent the averages of our function f. And I know it's very annoying that there's f's and f's, but at least some of my f's are gray and others are black, so the gray ones are variables and the black ones are actual functions. So this is what something like this looks like. So usually this will have a domain, a range, and certain derivative conditions, and convexity or concavity. And I want to just attract your attention to the very last line. I think we can all agree on the derivative of this function b in m. Okay, so we're going to get f squared divided by 1 plus m squared. So now, since m represents this sequence of alphas, and we have the Carlson packing condition, we know that it favorably compares with 1. So we can get rid of the m in here. We can just say, okay, this is bigger than or equal f squared divided by 4. So this enters into the proof. It now doesn't matter exactly how, but this is the same 4 as you're seeing in the estimate. So I'll come back to this later, so don't forget this nice estimate of the derivative. So our theorem about the Berling operator, where I said one can almost say it almost easy, okay, because it can be gotten from the dyadic estimate. So you can invent, one way to get it is by this idea of using the heat equation and extrapolation, where we will be able to, also with the Bellman function, but this time plugging in heat averages, we will get the estimate in L2 for the Berling operator. And we will also get it in LP, which was important for the application. Now I want to mention that Oliver and Sasha have an alternative proof for this, also with the averaging technique, where you don't have to use any heat extensions. And their proof is very interesting, because it has incredibly good constants, also when there's no weight. So, and here very briefly, the reason why this had applications in complex PDE. So the Berling operator has one nice decisive feature, namely it turns d derivatives into d bar derivatives. Now, best functions are the ones that are analytic, when the d bar derivative is 0. Functions that aren't quite as good, but where the d bar derivative is compared via an L infinity function to the d derivative, are almost as good. So these are some of the origins of the so-called Beltrami equation that you see on the left. So mu is going to be a small L infinity function, and you're asking that the mu times d bar f is equal to df. This is some control on the d bar derivative, and mu is 0, you get the condition for analyticity. So these are important generalizations in complex PDE. And so the K has a geometric meaning. So when analytic maps map small disks to small disks, these kinds of solutions, the homomorphic solutions, will map small disks to ellipses, and the eccentricity of the ellipses has to do with the L infinity norm of this multiplier mu. So now it was an open question. What was the minimal requirement of a priori regularity of f, which then guarantees that the solution actually self-improves to be in W12. Like, let me say, if such a solution is in W12, it's very nice. It's usually continuous and everything. So the case for P bigger than 1 plus K is due to Astala, Ivyanec, and Saxman. And then the borderline case is due to us and needed this estimate, this sharp estimate for the Berling Alfors operator. So some people say this is why weights became popular, but I don't think so. Personally, I don't. I mean, we've done plenty great things, but this was a nice application. So then the Hilbert transform. To my taste, a little bit more difficult. So this same trick with heat extensions won't work, because the Hilbert transform wants what it wants, the Berling operator wants what it wants. So here the first proof of the Hilbert transform used this averaging technique, but a baby version. Okay, it didn't use the full averaging technique developed by Nazarov, Trail, and Wohlberg in their non-homogeneous T of1 theorem. This is the kind of thing a beginning grad student can come up with. So there is the idea that if you change the grids according to the invariance properties of the Hilbert transform, you can actually average in such a clever way that you get the expression for the Hilbert transform with a non-zero multiple. So this is a little bit a visual for those people who know the proof. They will be reminded now, and if you don't know the proof, you will be reminded of nothing. So, but you will know that the Hilbert transform has 3 defining properties, and you can force almost anything on an object by averaging. So you just force it to have those properties, and out comes the Hilbert transform. So this was developed for a different problem, not really for the weights, but with some substantial extra effort, one can get this weighted estimate. And for me, at the time, this problem was very challenging. So, because the Bellman technique, it doesn't love this operator. So it obviously doesn't hate it either, because we could still use it, but it doesn't really love it. So what the Bellman technique wants to do, it wants to estimate increments at the same time, like dyadic martingale differences of 2 functions f and g paired together. If you're going to split them, you're going to ruin your estimate. So they need to be glued together. But if you're trying to estimate this dyadic shift, you have this split in different times, and to overcome this, needed a new idea. So this new idea was in this paper, and this idea was developed, okay, very much developed by I don't know if it's really from this idea or if they had their own approach, but Oliver and Sasha have some wonderful ideas like this also, where you can then pair different things that the Bellman function does not want to pair together. And exactly, so now if you do not want such a beautiful representation for the Hilbert transform, just taking one generation prior. If you're willing to wait many, many, many generations, meaning having infinite complexity, then you can get the same representation formula as a corollary of the homogeneous part of the non-homogeneous T(1) theorem by Nazarov, Trail, and Wohlberg. It's going to look different. And also, there is an improvement of my way to estimate with Bellman by Reznikov, Trail, and Wohlberg, and by Trail in even tighter. And they together, they allow to fully generalize the estimate obtained by me on the Hilbert transform. And now, fast forward. We now are in the sparse domination. And here I want to take a little time, because the quantifiers are so weird. Okay, so let's first agree on what a sparse collection is. So if you want to know what a sparse collection is, you want to look at the picture at the bottom of the slide. So you will see black intervals and then red intervals. So the black intervals, they represent the sparse collection of dyadic intervals. So the defining characteristic is the red part, which is what is left over if you compare with the previous black intervals. And this has to have at least half of the mass. So the red ones are a large portion of the previous interval. So on the left-hand side, you see a very simple choice of sparse collection. On the right-hand side, you see a little bit more complicated one. How do you get those sparse collections? So basically, they arise with a dyadic stopping time procedure, where you start on the top, and you will run your objects, and you will decide, well, how often do they double? And if you have good a priori estimates on your operator, you know that it doesn't double very often. So if something doesn't double very often, you will get a sparse collection. So the black intervals are obtained by looking at the action of your operator acting on your function or of your martingale. So what do you get from this? You get this completely crazy looking inequality. So T is a singular integral, such as the Hilbert transform, or it could be this T sigma operator. And so there exists for all f separately such a sparse collection, so that almost surely you get that Tf of x is bounded by a constant times a sum of positive quantities. If you have a cancellative operator, this is a crazy fact. But why does it work? Because it says for all f there exists. Okay, there doesn't exist the S that works for all f. It's never going to happen. But since you personalize this, then you can estimate. So this is for analysts a very strange way to do it, but it's extremely useful, because after all, if you're trying to chase an estimate, you don't really have to use exactly what this sparse collection is. As long as you know that it's sparse, and as long as you know that this is enough and you can estimate it, you'll have all your f's covered, no matter if you had to personalize this. So this arose around 2015, not completely out of nowhere, because I said earlier there was a predecessor of this studied by Perez and Lerner, for example, very good mathematicians too, and then it was developed into this so-called pointwise domination by the people underlined in green roughly at the same time. And I want to point out, these are just monsters. I mean, you know, Nazarov and Lacy. and among them Conde and Ray. And Ray was a very young student of Sasha's at the time. So this is a big accomplishment to be able to keep up at this time with these people. So I think the one that is most used now is the one of Lacey, because it's the most probabilistic one, top-down approach, very simple. Okay, so now, what is not working when there is a matrix weight? Now, you promised me that you would retain that derivative. So this derivative of f squared divided by, well, there was a 1, now there's a w, but let's get over that, of w plus m squared is going to be bigger than or equal f squared over 4w squared. That's why I like this iPad. So, okay, so now, what if you have a matrix Bellman function? So you also want to make this m disappear. You want to say, okay, previously we compared the m to the w and we made it disappear and we got this constant 4. But now the situation is terrible, because you have w plus m inverse, you have the increment of m, and you have w plus m inverse again. If you know anything on the norm of, or the estimate of w plus m inverse, it doesn't help you at all with estimating this. Okay, so you cannot get rid of this m. And there is, again, very clever idea due to Nazarov, Trail, Wohlberg, and Nazarov, Trail, Wohlberg, Pizier, and later elaborated by Coolidge and Trail, that will make this m disappear. So this is an issue that was, one could circumvent it to some extent. What is the issue with sparse domination? So when you run your stopping times, as you know, if you're running stopping times, you want a quantity that you can actually stop. So you want to stop on an interval, and then you want to basically have a self-similarity situation. You want to start over on this interval again and run your stopping time again to get your next stopping time. That's how it usually works. Now, the matrix weights mess with this in a very horrible way. So here is my attempt to try to explain how this happens. So if you, for example, apply a maximal function of sorts to a vector function, doesn't really matter right now which one it is, and you want to then estimate it in L2 of W, you have, if you're applying a maximal function, you're getting a scalar quantity, and you're going to have a very hard time measuring it with respect to a matrix weight. So what's usually done is the incorporation of the weight before you take the supremum in your maximal function. And this is horrible, as it turns out, because you have this pointwise multiplication, W of x, and you're running your supremum, and things can change very drastically. So this W of x multiplication in the supremum is messing horribly with your situation. So what this means, if you're trying to localize your operator, you just cannot. So you either get a completely nonsensical thing that's not a stopping time, or you have a price to pay. So if you make it stoppable, you usually use some power of the A2 characteristic. So this is at least meant to explain why things are so terrible. And here's a list of what is going on, and what is bad and what is good. So the matrix-weighted Carlson lemma was true after all. Took also a long time to prove. It was done in 2015 by Coolidge and Trail with elaboration on the Bellman technique. Then a useful bilinear weighted embedding Carlson lemma, whatever that is, it was important in the early estimates, is false with the most idiotic counterexample in the world. And a useless version is true. So the useless version is also sharp in the sense that it cannot be improved at all in its complete, beautiful uselessness. It stands there. So the bilinear Carlson lemma doesn't work at all. Now, the maximal functions, there has been an early good estimate by Israelowitz, Kwon, and Pott. And then later, there was an example by Wohlberg. Was it with Sergei Trail? I think so, where you also showed that 3/2 is the best. And then there is the sharp matrix-weighted square function that we did at MSRI. The square function has a linear bound, sort of re-emphasizing that maybe the Hilbert transform should too. And then we looked at one point to a weighted maximal function, one that is more like the Dupes inequality with absolute values outside. So you take your martingale and you take the absolute values and take your supremum, or the Littlewood-Paley maximal function, where you tend to take the absolute value and first and then the average. So those have reasonable definitions when there is a matrix weight, and one of them is bounded and one of them is not bounded. Now the boundedness is by me and Pot and Regera, but anyone could have written this. This is just a survey paper. It follows directly from the Carlson lemma. And the example of us with Nazarov, Schreb and Trail is quite substantial. So the counterexample is difficult. The positive result is not. So what is a method that somehow at least worked a little bit is the idea of the convex body sparse domination. So the question is, how do you replace absolute values that you have in scalar functions when you have a vector? If you just put the norm there, it's not going to be a vector anymore. So you want to replace the absolute value, but you want to maintain a vector. So the idea is the following. So if you compare the average of f with the average of magnitude of f, then you basically look at the average of magnitude of f minus the average of magnitude of f and this entire interval. This entire interval can be represented as simply multiplying f, let's say by the signum of f or something like this, inside the interval to get the right-hand corner or the left-hand corner, and you will be able to get every single point in this line between minus absolute value f and f. So the same idea in the vector case will give you a convex body. Not quite, but if interpreted correctly, it will give you a convex body. So what replaces absolute value of magnitude f is a convex body. And via this convex body, we managed to write a sparse domination with the help of the Minkowski sum. So on the right-hand side, you have all these convex bodies. It tells you where the vectors Tf are located. And this is an object one can more or less work with, but no matter what we did, we got 3/2 estimate. So now, what's even worse? When the sparse collection was a completely unrealistic sparse collection, when it was a simple sparse collection, so that each interval only has one descendant, then our estimate with matrix weight became power 1. So why is this bad? Well, because on one hand, it never happens. And secondly, these are basically all your scalar counterexamples. Okay, so these are all your scalar examples for optimality. They look like this, and here this example is out. So it looked like a dead end. But then what we did is the following. So yeah, this reminds me of a story of a friend of mine, Janine Witwer, who is roughly of my age. So she eventually stopped doing mathematical research, but she was very good. So she solved this problem with the T-sigma operator. And I know from her that she was told to show that the Hilbert transform in the scalar world had a 3/2 bound. Okay, and the way she was told for 1.5 years to try to pursue this example is to list a lot of power weights next to each other and try to get a blow up. It of course wasn't going to work because it's a scalar world and we know that it's power 1. But the reflex of Robert Pfefferman was somehow correct. Okay, it's just that if you are going to try to write down an explicit weight, it's just not going to happen. So if you want to take the regular counterexample, that gives linear and you want to make it worse, and you list them very tightly together and calculate explicitly, you're going to lose your mind. So therefore, our first step was to think about what the classical counterexample for the Hilbert transform, the scalar weight, are the power weights. So you just take a power function x to the alpha, let alpha go to 1, and as a test function, you take the inverse. And then you can just compute everything. You can compute the A2 characteristic, you can compute the weighted L2 norm, you can compute the Hilbert transform on this F, or at least estimate it from below. So, and then you will see very quickly that power 1 cannot be improved. So what's to do here? The first step is to say this very explicit, very simple example should be made into a martingale example. So this is achieved by starting a weight with a constant and then making it act like x to the alpha. So it means that most of its mass will be put on one interval and the rest on the other. So the black interval is going to be the big one, the green interval the small one. And on the green side, you just have to do one more step in order to get a weight. And with the left side, you continue and stretch it and stretch it. It looks a whole lot like this power weight. And you have to stretch the value of this quantity by 2 minus 1 over q, where q is the A2 characteristic. So if the A2 characteristic is very large, you will stretch it by almost 2. If you want to maintain positivity, you realize you can at most stretch it by 2, obviously. Okay, so this is a very extreme stretch. And this gives you the same calculation as the power weight, but in a martingale world. And based on this, in the vector world, we already know such a situation with sparse intervals that carry all the weight, that's not going to work. So we need something with infinitely many singularities. So the infinitely many singularities are brought to the game through the idea that, or the well-known fact that matrices are not scalars. So in, let's say in a 2 by 2 case, you have a matrix, it will have its two principal axes, its eigenbases, and its eigenvectors. So we start with a relatively disbalanced situation. One eigenvalue roughly 1, the other eigenvalue roughly epsilon. So in the first step, what we do, we rotate ever so slightly the situation. We rotate the basis. We're going to get our descendant to the right, our descendant to the left. And after this rotation is completed on one hand to the right and the other hand to the left, that's when we will perform the stretching of the eigenvalues, similar to the scalar case. So that in every second step, there is the equivalent of the scalar case. In every other step, there is the essence of the matrix. So you'll be able to get in this manner a weight with when you continue will have infinitely many singularities. Almost what this Robert Pfefferman suggested in a way, to put these together, only that it really does not work in the scalar case. So this weight is someone's counterexample, but whose counterexample? So it turns out it was not the counterexample for the T sigma operator, it was the counterexample for the dyadic shift. Okay, so we see again the dyadic shift, and we found that the dyadic shift has a 3/2 estimate. Now, the conjecture was on the Hilbert transform. So now this brings me back to my first visit with Gilles Pizier in the year 2000 that I want to share with you. So I was invited to College Station. I go see this very brilliant, scary mathematician, and who wanted to talk to me the whole week, all day. And he was very intrigued by this Haar shift and wanted to talk about it a lot. And he asked me many questions, and most of them I did not understand, but now that time passes, I understand more and more of those questions. So one of the questions was, well, Stephanie, how about lower bounds? I was thinking, come on, what have you been smoking? So we are talking about a convexity argument, right? So we estimate the dyadic shifts, and then everything in its convex hull will also be estimated. But that doesn't work the other way around. You're averaging something. So I was thinking, what is wrong with him? So, well, it works. So there is, because, there's this other paper by Bourgain that did something like this in a very different setting. And then over the years it was developed by Nazarov and by Trail, and also by, actually by me and my husband Komla. We've used this idea to get lower estimates, and this is also what we do here. So we have something for the Haar shift. It's a lower estimate. Averaging is not going to help, but this idea of so-called high-frequency modulation does. So this is fantastic. Again, one of my absolute favorite papers, 1982 or 86 by Jean Bourgain, where he proves that UMD is, you have a UMD space if you know that the Hilbert transform is bounded. So basically he estimates the martingale multiplier by the norm of the Hilbert transform. It's exactly a lower bound. So with weights it's very, very different. A lot has to be modified in order to get to the weights, because Bourgain's technique is very translation and dilation invariant, which with weights you don't have that. But we use this technique. It's kind of a nightmare. And as you know, the Hilbert transform wants what it wants. So it didn't want just the dyadic shift. It wanted a combination of a whole bunch of dyadic shifts. So lucky for us, it was hanging by a hair. So a very scary moment when we realized we needed also minus the adjoint. So basically what we had here was a constant minus something else, and it was the same constant but with the opposing sign. Thank God. Otherwise we would have said, okay, Hilbert transform is larger than 0 times the weight to the power of 3/2. So different shift operators were involved, and we could run this high frequency modulation and so obtain the counterexample for the Hilbert transform. And I think this is now the end of my talk.
Can I be heard? No. Just about you with the mic. Can you hear whether the mic makes any?
It's all that you will be heard
It's
from
on.
mine. So,
Okay.
yeah.
Well, anyway, please, questions? So we're not
for like some other operators like Riesz transforms, or is it like one can repeat the same thing?
Well, for Riesz transform I haven't tried, but I would imagine it works for Riesz transforms. So the reason why I'm saying it is because, we did it for the Banach spaces with Komla. We have a model for the Riesz transforms, and this gave the equivalence of the Riesz vector in the Banach space setting, also with this high frequency modulation. So I'm guessing this would be a way to look into if this would be even an interesting problem. I'm guessing the Riesz transforms should work.
So any operator which is not either 1 or 3/2?
No.
No.
I mean, look, we are just so happy that this problem is done. To be honest, we had with Breitwig and Kelly Pickle, we had 3/2 and logarithms, and one of those logarithms could be gotten rid of, and then we got rid of another logarithm. There is one actually. Now that you're asking about it, I don't know how to prove it. So there's this Dupes inequality, and that was independent of the weight, and then there was this convex body maximal operator. This could be logarithmic with A2. What do you think, Sasha? our counterexample spits out logarithmic with a2. So, but unfortunately, I have no idea how to prove it.
Okay, so then thank you again.
Now we have a coffee break, and we go across the street. Just follow the organizers.
Ago, I deal with spectral operator theory, functional models, and so on. But now I completely in this subject in Bellman function technique. And my aim for today is to try give you an impression what Bellman function is and how it works. Of course, no mathematical talk can be without some theorem. Therefore, formally, I present a theorem at the very end. And it was a theorem proved together with my colleagues Dima Stolerov and Pavel Zatitsky, and it is just about comparison to external problems. I explain what problems I will speak about. But some mystery is that there is no direct connection between these problems, and we have no clear explanation why the answer is the same. We can prove it only using finding the Bellman function for one problem and Bellman function for other problem. They are not equivalent in some sense, but there is something that we could, how we could compare to this function. And the result is that in some critical line where we need to get the value of these two functions to get an estimate, they are completely coincide. And this mystery we cannot explain in other way. Of course, there should be some explanation, but I use this pretext to explain what Bellman function is and how it works. So, and I start with usual notation and the explanation what problems are. No, first of all, average is already such a angular brackets used today, and BMO is very popular space, but here we use L2 based norm for BMO, not usual L1, but L2 is more convenient, and namely this expression, average of square of difference between function and its average. But it's of course not a norm, but we have to factorize our constant functions to get a norm, but it doesn't matter. So very important for us will be such expression, such presentation of the same expression. Average of square minus square of average. And one more notation is epsilon ball in BMO. So, and problem is the following. We are given some real valued function f, and we would like estimate this integral functional over unit ball of BMO. Test function phi runs over unit ball in BMO. And here is immediately definition of what is Bellman function in this situation. In fact, what we need only to get a number and estimate this quantity. But instead of this, we would seek for a function of two variables. Variables is in fact in our disposition, and, but here is convenient take to fix average of function. This will be x1, and average of its square of function will be x2. Why? Because this is a component of the norm. As I told, x2 minus x1 square gives you supremum over all phi, gives you a norm. And we consider the function from unit ball. So it's some clear, I hope, definition, nothing special, and special is in properties of this Bellman function. I will mention this property, of course, without any proof. I only underline what properties are simple and what properties are non-trivial. Of course, the simple property is that, in fact, this Bellman function doesn't depend on the interval where it is defined. It's crucial for Bellman function, but it's very simple because linear transformation of the interval, you could reduce your interval to 0, 1, and it doesn't matter. Domain of our function will be such a parabolic strip. Why? Of course, formally function defined on the whole plane, x1, x2 can be taken arbitrary. But if you take out of this strip x1 and x2, you cannot find a test function phi with such a x1 and x2 because from the left it's simply Cauchy-Schwarz inequality, and right is the norm of a function is less than 1. You see x2 minus x1 square is less than 1. So it's also outside of this strip, for your formal function is minus infinity, because the set of test function is empty. So it's not interesting for us. Only this, we consider the function only on this domain. Another simple property is the boundary value of the function. We know the function on the lower boundary. Why? Because when occurs equality in Cauchy-Schwarz inequality, when the vectors are parallel, in fact, when the functions are proportional. Therefore, if x2 equals x1 square, then function phi is a constant function which is x1, therefore. Constant function is x1. It's only representative of the set over we take a supreme, and therefore the answer is known, is clear, is f of x1, nothing more. No? So less trivial property is the concavity of Bellman function. If the problem would be dyadic, this concavity is rather simple and can be, but in non-dyadic setting, it is non-trivial, rather non-trivial, but it is a theorem that a Bellman function has to be locally concave. But in fact, this list of properties, it's not obligatory, how to say, to prove that they are fulfilled. We look for a function that satisfies this property. And if we are succeeded, then some machinery gives you an estimate, some estimate. Maybe it is not sharp estimate if we don't satisfy all the property. But nevertheless, sometimes it could be sharp. For example, Stephanie gave an example for Carlson embedding theorem and called this function the Bellman function. But it is a super solution. It is some function which is greater than true Bellman function. But nevertheless, it gives a sharp constant, because we only need one number, not the whole function, to get inequality. And so, and Bellman function, of course, is minimal among all such locally concave function. But with specific properties that concavity should be degenerate at any point of the domain. Maybe strictly to prove it requires some consideration, but to explain it's why it's so, it's rather simple, because if it's strictly concave in all direction, we could cut this cap and find a less function which is less than given first our concave function. But therefore, it has to be degenerate in some direction. What I mean degenerate, that it simply is linear. No, it's a bit further, but degenerated means that Hessian of the matrix, its determinant is 0 at any point of the domain. And so we come to the Monge-Ampère equation. So we know what to solve to find our function. We need to solve Monge-Ampère equation, and for this boundary value we need some intermeds, I could give you some examples. It's not obligatory for what follows, but what examples could be some specific function which we use to, for example, exponential function give you integral form of John Nirenberg inequality. If you take 2 rays, you estimate tails of test functions. Therefore, in such a way, you get classical John Nirenberg inequality. And one more example, it's if you take power s to the power p, this means you estimate equivalence between LP-based HP, BMO norm and H2-based. It's known result that all such norms are equivalent, and definition of BMO doesn't depend on what P you take, but nevertheless, sometimes it's interesting to quantitative estimation. So now we return to our problem. What we need to find? We would like to find function b satisfying this boundary condition. On the lower boundary is our given function f, and which solves homogeneous Monge-Ampère equation. Now I consider this problem and begin to describe another one, because in the second part I will try to explain how we will solve such equation and different equation which appears for the second problem. The second problem is the following. First, formal probabilistic setting. If you have standard probabilistic space, you have filtrations there, and 2 martingales adapted to this filtration. One is martingale transformed to another. What it means that the martingale difference are equal in modulus. So they differ by a sign. And the problem is to estimate expectation of f of psi infinity, where f is just arbitrary function, like in the first setting on BMO, provided phi is the indicator of an event. This means that phi takes 2 values, 0 and 1. Yes, but for our aim, it will be a bit more convenient to consider a function which, for symmetry simply, that take value 1 and minus 1. So now I give another setting, function theory setting, I call it, so we take a function which take value 1 and minus 1 and consider its hard decomposition. And if we change arbitrary signs of, simply consider alpha as a Haar multiplier with the value plus minus 1, we get martingale transform of the function phi. And now the same problem is to find sharp estimate this average f of phi, provided alpha n are arbitrary sequence of signs. It seems that these two problems have no common. But let us start to consider the Bellman function for this problem. This is a definition of the corresponding Bellman function. We take phi, which is average of phi is less than 1, and psi, we don't know, is arbitrary. Because psi is martingale transform. And we would like to maximize of this integral function. Again, Bellman function doesn't depend on the interval where our test function are defined, because everywhere averages participate in the problem. The second domain now is usual strip. Why? Because if we are on the upper boundary, that means that the average of phi is equal 1. And what does it mean? This means that it is almost everywhere is 1. Yes, because it take value 1 and minus 1. If the positive measure will be on the set where it's minus 1, then the average will be strictly less than 1. No, it's the same for the second boundary, x2 equals minus 1. And we know boundary value, again, because on the boundary, our function phi is a constant, plus or minus 1, almost everywhere. So therefore, in hard decomposition, there is only one term. And the result of the martingale transform where participate harmonics gives nothing. So therefore psi is simply equal to phi, and therefore the result will be f of x1. Now the Bellman function is diagonally concave, or as one from the how to say, the people who are at the origin of this subject he is called as zigzag concave. That means the function has to be concave in this or this direction. And again, Bellman function is minimal among such diagonally concave function, and concavity again has to be degenerated. In fact, by the same reason. Here it's a bit more complicated reasoning, but it's the same. Therefore, we have either one or second equation. Oh. What does it mean? Here is empty. There is somebody. Why screen is white? I without anything. No, I don't touch it. It may be something wrong. Press here, but everything disappears. To repeat simply, да?
Where is your presentation? Oh,
Here.
Okay. Microphone disconnected.
No, here it is. Ljubljana is here. Control L. Oh, full screen. I'm very sorry. Mm-hmm.
Should work now.
Thank you very much. So where we are? So in result, we come to the following boundary problem as well. So it's our boundary value, and this is the equation we have to solve. In fact, it's a product of these two expressions, and it looks rather horrible for solving, but it means nothing. Then it's linear second derivative along one diagonal, or second derivative other diagonal is 0. We simply have to change variables, x plus 1 and x minus 1, take new variables, and then we could, instead of this expression, we get product of two second derivative along. And so it is not a big deal. No, as I already said, that this is linear along this direction, and in fact, this is crucial property to search to look for Bellman function. And here appears such a notion as a foliation. In the second case, our strip could be split in three type of different behavior of where the function is linear. Namely, when is linear in direction x1 plus x2, when is in opposite direction, or it's bilinear. Here it is trivial. A bit less trivial is that in for Monge-Ampere equation, if rank of Hessian matrix is 1, therefore we get a vector field, and integral line of this vector field always are straight lines, and therefore we can foliate our domain, our our parabolic strip where the Hessian is of rank 1, therefore they are linear in some direction, so we have an interval of a straight line where along which on which is our function is linear. This in fact it's not obligatory. We cannot how to say foliate our domain with different small pieces of intervals. In fact, obligatory one point of this extremal line is on lower boundary. So we have only two types of integer such extremal lines. Either both points are on lower boundary, or one point on lower boundary, the second and the point is tangent to the upper boundary. To prove that it has to be tangent, it is also not quite trivial, but nevertheless it's so. And where Hessian is 0, therefore B is simply a linear function. So when linear in two directions, then it's linear. And our aim now is to construct to foliate our domain using this knowledge. And after we have found the foliation, almost everything will be done, because when knowing foliation, we reconstruct Bellman function rather simply. For the chord connecting two points on the lower boundary of parabolic strip is trivial, because we know at what one end and the second end, and the function is linear along this. Therefore, we know it's everywhere on such part of foliation. But for example, for exponential is foliation of this kind. Nevertheless, also, if we can prove that foliation is like this, then we are done, because reconstruct Bellman function is also very easy. It's dependent up to a constant it has a slope of this function satisfies first order differential equation, and it's can be solved up to a constant. And if this foliation is goes to infinity, on the infinity this constant obligatory is 0 from other reason. And it appears that for the second problem, foliation like left tangent line, it corresponds, for example, the case when third derivative of f is positive. And the same situation, if third derivative is positive, we have such a foliation for probabilistic problem. Another example of foliation is a cup. As I told, there are some interval, some lines that along which our function is linear, and both ends are on the lower parabola. As you see, such cup could join parts with right tangent foliation and left tangent foliation. It's some necessary intermediate gluing foliation. And it appears that very simple, we call it cup equation, gives us answer for the which point A and B could be ends of extremal intervals. And origin of this cup always is a point where third derivative is zero, and third derivative change is its sign from minus to plus at this point. And a bit more strange foliation is here in the strip. Again, we have two herringbones, horizontal herringbones, that we attempt to join in a way. And now we use put between these two herringbones vertical herringbones. And what is the question is how to find at which point A and B these lines meet each other in the same point of the what herringbones have how to хребет, да? I'm sorry. No, but from the picture is more clear than I try to look to find appropriate word. But the interesting thing is that here we have the same cup equation. That relation that explain us which point could be ends of the corresponding bones, and bones start at the same points in sense where we could construct a cap for the parabolic strip. In fact, it was the first moment after solving, in a sense, completely the first problem and describing solution in 2 or 100 volume paper. This will our independent job to try to solve this probabilistic to estimate martingale transform. And this was the first signal for us that something is strange, that the equation is the same. There is some correspondence, therefore. And we try to correspond one foliation for the parabolic trip to the corresponding foliation in the usual trip. The main thing is the number of different possible foliation is finite. So we could step by step to check there is correspondence or not. And one more foliation when we join our tangent foliation in other order, not as in cap when foliation goes like that. But here between these two foliations is the angle where our function is linear. in the strip, the corresponding figure of foliation is also two herringbone, which joined by a square of bilinearity. I'm sorry, I show a bit maybe more complicated foliation. I will not list all possible foliation, but nevertheless, now tangent foliation changed its direction twice. One after the cap, and the second time after the angle. And in fact, we consider this picture in dynamics. No, we don't fix width of strip. It's taken of its epsilon, and we consider how foliation changed when we strip make wider and wider. And it appears that cap is stable because point C is completely definite, but angle is moving when when upper boundary goes up, and it could happen then it's touch the cap, and such a figure appears. We call it tribal, but it is by some strange reason it doesn't matter. Again, domain of linearity, and it was how to say crucial question: find the corresponding situation in the strip when we have vertical herringbones that connect to horizontal herringbones and square of reality which connect another two. And what happens when square come to the? It appears that it's rather easy. Such a figure appears as a corner, and even when we make strip more. Not 1 minus 1, but wider and wider, then this corner can be disappear at all, and will be one herringbone for large strip.
So here it goes like zigzag.
By this reason, it's probably was how to say. No, that doesn't matter after that. No, and finally, the main result. Rather long paper comparing these various kind of foliation and the dynamic when the strip is enlarged. The following is true that for arbitrary boundary function f, what is important? That f is arbitrary, but Bellman function on the upper bound of parabolic strip is just the Bellman function for the second problem on in the middle of the strip, usual strip. And this is immediately our 200 papers replaced for this second problem. That it's not obligatory to make all machinery to investigate all possible foliation. It's sufficient to for us would be to show that there is one-to-one correspondence between foliation of the first problem and the second problem. No? And these are two papers where the first problem is described, And this is a recent paper with Stolarov and Zatitsky, where we found this, when we proved, in fact, not found we a bit earlier, but when we will be able to prove this correspondence between two folations. And so I finished. Thank you very much. Wait, I'm sorry. I shifted. No?
Maybe the explanation is that sort of extremal sequences for the first problem, BMO problem, are just functions from BMO which are just, I don't know, harmonic conjugate of your plus minus one functions.
I'm not sure. In fact, we have some ideas related with Brownian motion, where we, instead of, how to say, extremal function to find, we could consider Brownian motion. And they have more clear, how to say, connection in one case and in another case. But
extremal functions should be very interesting.
But we know extremal function in any case. We could write down for the parabolic strip. All cases are written very carefully. Explain how it is, for example, interesting how to goes such extremal function, for example, through this trolleybus.
But maybe there are several different.
Sometimes yes, but sometimes it's unique.
And you cannot look at BMO function and say, oh, that's an interesting function. But it's you make it integral, and suddenly you see that it has only two values. It's a very interesting function, right?
Mm-hmm.
So maybe this is what happened.
So I let people think during, and in the meantime, I'll ask a stupid question. When, like in the trolleybus, when there is a square, an empty square, does it mean that the function is linear there?
Linear inside, yes. Inside this domain.
Okay, so it's a connection between two
between
regions with different slopes. Okay.
Different chord and tangent.
Okay. Thanks. So now you're even allowed stupid questions? No?
I have a question, but mine will be incomprehensible, so I'll try. So I'm sorry, my question will probably be way off. And so I'm wondering, you know, when we had the dyadic increments,
yes,
they are a little bit like harmonic increments. Okay, so if you now do, and then it became convexity or concavity in the Bellman function, and it led you to Monge-Ampère equations and all this. So my question is basically, what if you restrict the increments you're allowed to have? If you now have a pair of functions and you have not any dyadic increment, but they are related by a means of a rotation, like on an analytic function. So do you have a model for your Bellman so that you know what the good solution is? So that I don't have to lie about having a Bellman function that's not?
Yeah, yes. I understood. You see, maybe it helps more recent, even not published investigation by Pavel Zatitsky, how to solve in parabolic strip arbitrary dyadic problem, because for exponential it is a lot of work. In other words, if we if you find some more or less clear correspondence between dyadic and non-dyadic behavior of how to say extremal increment, in what the direction we have when we have to jump, for example, and where we are continuously. Maybe it would be, it gives some idea to how to what to could be related to the harmonic questions. But now I cannot say anything.
Any more questions? Okay, then let's thanks Peter.
Just say one thing.
Я ушел, и никто меня не поправил. Я стал говорить, что я здесь.
Не беспокойтесь, все в порядке.
Ничего, да?
Ничего.
Ну как, запись какая-то там идет.
Мне кажется, что
Он
да,
нам добавил
можно
звук.
регулировать.
Понятно.
So now we have a lunch break. Those who signed up for lunch at Vodnikov Hram can follow Alexei and myself in that direction. If not, well, you are on your own. And we resume at 2:40. Thank you.
Who? Okay.
Boh. It's on.
Okay.
So good afternoon. Let's start our afternoon session. Our first speaker is Professor Zoltan Baloch from University of Bern, and the title of his talk is LSI via OMC and curvature. Please.
Okay, thank you. So I would like to thank the organizers for inviting me, especially Oliver. Thank also Sasha for turning 70. It's always a good way to celebrate. For me, it's very special because, first of all, I see Sasha since many, many years. And also I had the chance to meet some of my academic siblings and also my academic grandfather. So this is a really great occasion. Okay, so the conference is about harmonic analysis and related areas, and I'm more in the related areas part. So the talk is about LSI. This is logarithmic Sobolev inequality, and I show you a proof via the optimal mass transportation. So that's a method which I'm very excited about it. You can really prove some inequalities which are really sharp. So I would like to explain you this method actually, how it works. Okay, so actually I sent an email to Sasha previously and he assured me that he likes LSI, so I'm very happy about that too. Okay, so here is the structure of my talk. So I consider in great detail with a full proof actually of the method of the optimal mass transport, how to apply it to prove the LSI in the Euclidean case, right? So you can even take notes if you want, because I present, all the details. And then I try to sort of adapt the same method with a little bit of hand waving to other geometric situations. Like, so I go a little bit gradually here. We consider the Euclidean spaces with a weight. And then we consider curved spaces with false-stiff Ricci curvature in a synthetic sense. I will explain this, what does that mean. And this is the so-called CD0n spaces. And then you will see that this is related to the isoperimetric inequality in the same kind of framework. And then we'll look at the situation when you don't have a lower bound on the curvature, and this is the so-called Micah-Simon inequality, especially the new version, or the sharp version, which has been kind of proven lately by Simon Brendle. And then and the last part of my talk is actually the main result. What I would like to present is this so-called Micah-Simon logarithmic Sobolev inequality. So this is a logarithmic Sobolev inequality on embedded manifolds in a higher dimensional Euclidean space. You can think about like a catenoid, for example. Okay. So let's go with this program. This is a joint work with my longtime collaborator Alexandru Cristai and two younger colleagues, Sebastiano Don and Francesca Tripaldi. Sebastiano and Francesca were postdocs in my research group at the time we did this research together. Okay, so this is the inequality we want to prove, and on the left you have the entropy of a probability density, which I call it F squared, and we want to control this entropy from the right by the energy of the function, by the Dirichlet energy, and the logarithm of this. This is the so-called Euclidean LSI, Euclidean logarithmic Sobolev inequality. So you might know this version, or you might know an equivalent version of this LSI, which is, instead of having here the Euclidean Lebesgue measure, you maybe have the Gaussian measure or something. But this is somehow equivalent with this. And it was first proven by Leonard Gross in 1975, so it's more than 50 years ago. And since 50 years, there were lots of proofs of this inequality. And according to Michel Ledoux, he said there are at least 15 proofs, and he wrote a paper actually listing all these proofs and the main ideas. So I present now proof number 16, and I will try to convince you that it's good to have a 16 proof because this one you can maybe adapt it to a more general framework, which the previous ones might not be able to. So let's go to the proof. And the method of the optimal mass transport is the following one. You consider two measures with densities, so absolutely continuous measures with respect to the Lebesgue measure, called one of them mu, and this is the density is f squared. This is the function you want to kind of control by its energy. And then you look at the standard one, which is the Gaussian, okay? And I would like to consider the Gaussian with some parameter alpha, and you will see that this parameter alpha will play an important role because later we shall optimize in terms of this alpha. Okay, by the way, these are very beautiful numbers here, right? So it's of course n is the dimension, 2 is a very beautiful number, pi is and e as well, and I will explain you how this kind of numbers come into being to play a role in this inequality. So watch the appearance of these numbers in the proof. So the first one already appears here because we want the nu to be a probability measure. So we need to fix this constant such that it integrates to 1, and therefore you get the value of this C alpha to be alpha over pi, and that's the reason why pi appears over there. Okay, you will see later. Okay, so let's keep in mind this constant here, and let's go on. So what is the essence of the optimal mass transport? This method, actually this problem goes back 200 years to Gaspard Monge, who considered the following problem. He considered all the transformations T from Rn to Rn, which pushes a given measure, the push forward of mu, it's another given measure nu. So you should think about mu, the chosen one we had with the f squared as a density, and nu the Gaussian, okay? And what you want to do is to optimize this, this cost of transforming this x to tx, right? And we integrate with respect to mu. So this is the cost, and then you optimize with respect to all these transformations. Of course, this kind of problem is not well posed because for any measures, right? Because if you just consider mu to be, for example, Dirac delta, and nu to be maybe, an absolutely continuous measure, the T cannot split the mass, right? So you don't have any map at all which maps one measure to the other. But for absolutely continuous measures, it works, and actually there is a theorem of Jan-Brenier from 1980, so almost 150 years after this problem of Monge. Probably there was 150 years here needed because the problem was not well posed. And and then there was Kantorovich who relaxed this problem. We'll talk about this later, but that eventually led to the solution of Jan-Brenier, which says that there exists such a T which pushes mu to nu, and actually T has a very nice structure being a gradient of a convex function, okay? So which is excellent because then the fact that T pushes mu to nu in terms of densities, which is f squared, and the Gaussian, you can express it in this way, which is a Monge-Ampère equation. Okay? So imagine that this is a nonlinear equation in U, right? Imagine that you want to solve this equation, right? It's a very nonlinear, very terrible equation, but still Brenier tells you that there exists a solution actually of this equation. So if you look at from the point of view of PDEs, you cannot solve it, but from the point of view of optimal transport, if you look at in this way, then you can solve it. And I'm going to use this equation as a black box, as given, or as a solution, the existence of this u. Let's see how this helps us. So you remember, we want to kind of estimate the entropy of this f. So we might want to take the logarithm of this, and then we might want to multiply it by f squared and integrate and see if we can estimate. So the problem is that on the right side, we have this mysterious u coming, which we don't want to see on the right side. So we want to get rid of this at some point. So let's see how we do this. Okay. So the first step is to estimate the determinant, which is a nonlinear expression in terms of the Laplacian, which is a linear one, right? Like this. And here we really use the fact that u is a convex function. Okay. So the determinant of the Hessian is just simply the product of the eigenvalues, and then you just apply the arithmetic geometric mean inequality, or geometric arithmetic mean inequality, because here is the sum of the eigenvalues to write this equation. And then the next one is just a trivial equation using the expression of the exponential function. You can just think that e to the y is like always greater or equal than y plus 1, right? And y is this expression here. Okay. So then you can replace this by an inequality. The determinant you can replace by this equation raised to the power n. Then you have the Laplacian minus n. So let's do this on the next slide. Oh no, it's still here. Excellent. So this is the estimate we have. Okay. So how did we improve the situation? Not much, because you have still u on this side. Of course, a little bit less complicated expression as the determinant, and f on this side. So let's see how can we get rid of this u. Well, first of all, we need to take the logarithm. So I just copied this equation here, right? Now it's the place to take the logarithm. Okay, we do this. Then you get log of the constant, log of the e to the minus n, which will be minus m. Then you multiply by the probability density f squared, and you integrate. Well, on left side we get the entropy what we want, and here we get the constants, right? By this and this, using that f squared is simply a probability density. And then we have an expression because we multiply by f squared, remember, right? So we take the logarithm, then e disappears. This is what is going to stay. And then f squared is going to be multiplied here. So now the situation improved already, because now at least there is f somehow on the right side. And we want to actually see not f, but the gradient of f. Okay? So, so then we just need to integrate by parts here, right? This is what we do in the next step. Integrating by parts, instead of this one here, you get this expression, right? Well, okay, so great. Now we have the gradient of f appearing, but still this gradient of u is here, which we don't like. We want to get rid of those terms with the gradient of u. So what can we do? Well, the idea is to create a complete square where this gradient of u appears, and just ignore it. So let's complete the square. Yeah, this is the completing of the square. That this expression which appears here, you write it as a square minus this expression. And this is great, because then you can get rid of really this expression and have only f here. This is what we wanted. So let's do that. So I just copied whatever it was before, and then I ignore this square. So this is with minus, you know. So I can majorize this right side by simply ignoring this negative term, right? and I get something where only the gradient appears. But there is still no logarithm, right? So I want to see the logarithm, and that's the place where I optimize with respect to alpha. So at this point, I have an inequality which holds for every alpha here, okay? And I would like to consider this as a function of alpha and want to minimize it, minimize this function. So let's do that.
And why use this?
I got rid of all this part here, Sasha. You see, this is a complete square, so it's a positive term with a minus. So if I forget it, then I get something more. It's just arithmetics, right? Okay? So that was the trick how I get rid of you. Okay? So good. So now I can insert what the C of alpha is. So you remember that C of alpha was alpha over pi to the n minus 2. So then I insert it there. So I got an explicit formula of alpha where there is a logarithm appearing. So if alpha goes to 0, so if alpha goes to so if alpha goes to 0, this will go to infinity. This will go to minus infinity, but this will win. Okay? So if alpha goes to infinity, then this will go to 0, but this guy will go to infinity. So at 0 and infinity, you blow up at infinity, so it must have a minimum. It's actually, this is a convex function in alpha. Just differentiate in alpha, and you set the derivative equal to 0. So this is the function. This is high school mathematics already, or kindergarten mathematics, if you wish. Optimizing this in terms of alpha. This is what we do. We get alpha min is exactly this expression. And if you insert this value of alpha here and here, then you are going to end up exactly with this value. So that was the proof. So any questions so far? Maybe I make a little break to see if you would like to ask questions about this. Because
For Gaussian measure, it's approximately the same, but integration by parts is more...
yes, yeah, for Gaussian measure you can do the same proof. Okay, so that's a good question. So in this, that's a general philosophy of this optimal mass transport. You can prove not just the LSI with the optimal constant, you can prove the isoperimetric inequality with a sharp constant, you can prove the Sobolev inequalities with sharp constant. Always the trick is that, okay, so these are all known inequalities, and you already know sort of what is the extremal, and you choose as a target measure always the extremal one. So for the LSI, you choose the Gaussian. For the isoperimetric inequality, or then you choose the characteristic function, characteristic measure of the unit ball. For the I don't know, for the Sobolev inequality, you choose the Talenti function. You know this. So that's usually the trick too. As a target measure, you always choose. It's an educated guess, so to speak. Good. So, so it's interesting also that kind of you can trace back the equality cases. You can analyze that, and you can realize that equality holds if and only if F is a Gaussian. Okay, so I would like to now convince you that this proof works for, first of all, for general P's. Then this proof works for more general setting in Euclidean cones with log concave and homogeneous weights. Then it works in CDKN spaces. Okay, so it's not this proof, but the kind of the Gaussian one, or the, yeah. And then, and for CD0n spaces where k is equal to 0. So this kind of case is due to Lotte and Villani, and we pushed down k to 0 actually. Okay, and then there will be a different thing, so all these spaces are somehow positively curved in a certain sense, which I will explain it to you in a minute. But it turns out that it works also for submanifolds of Rn plus m, including minimal submanifolds as well. So, for example, the catenoid. Okay. Okay, so I would like to start with the theorem of, from, this millennium already, von Del Pino and Dolbo, who proved an analogous result, Euclidean Sobolev inequality, for p bigger than 1. Actually, they treated the case of p between 1 and the dimension, and so for some reason, I denote the dimension by big N. This is a kind of a notation in this CDKN situation. So anyway, so they proved a similar estimate. Here you have also a sort of a p entropy, if you wish, and then you can see that for p equal to 2, you can recover the same inequalities as before. Here you have a little bit more complicated constant, which looks like this, but if you put p equal to 2, you recover the same very nice, very simple constant. Okay, so so that has been generalized by us to the situation of cones, where you, instead of the full Rn, you have a cone, E, and there is a weight which is assumed to be log concave, homogeneous, and it has a certain degree tau. And then you should think that the new dimension is not n but n plus tau. Okay, so for tau equal to 0, when you have 1 here, then you recover the previous inequality. But in this way, this is a very kind of natural generalization of the previous proof. And you can prove it actually with the same method. I don't want to repeat the method, but maybe you want to read our paper. So I would like to now explain what do we mean, or what these people mean by CDKN, especially CD0n. So we put k equal to 0. So k is usually a lower bound of the curvature, and n is an upper bound of the dimension. Okay, so we look at spaces which are we look at the space of measures here with finite second moments, and this is a so-called Wasserstein space for some reason. And then we look at the entropy functional, but not the Shannon entropy as before, but the so-called Rényi entropy, which is just a negative power of the density of this rho. And then this curvature dimension condition CD0n, so I put k equal to 0 here, means the following, that in this Wasserstein space there are geodesics, right? Connecting two measures. And you look at, so this is a curve in the space of measures, and you look at what does this entropy functional do along these curves. And if this entropy functional turns to be convex in this way, then we say that that this curvature dimension condition CD0n is satisfied, which is a kind of very appealing condition for analysts, because it's a synthetic condition. You don't need to write down, the curvature tensor and explain what is a Ricci curvature and so on. But still, the first example of this kind of curvature dimension condition for dimension is for the Euclidean space with this, or Euclidean cone with this density here, turns out to be a CD0 n plus tau space, you know, so n plus tau is the new dimension, as I mentioned before. The next one is if you have a Riemannian manifold with positive Ricci curvature everywhere, then turns out also to be a CD0 n space, right? And these kind of things were proven by two parallel papers, one of them by Theo Sturm in 2006 and by Lotte and Villani in this, and that has been published in Acta Mathematica, and the parallel paper by Lotte and Villani was in the Annals of Mathematics. And this started a whole new area of mathematics, kind of looking at metric measure spaces satisfying this kind of curvature dimension condition. It turned out that with this kind of, you can do a lot of analysis on these spaces. So for example, you can prove, and Sturm did that, that this function, which is the measure of a ball divided by r to the n. So n here doesn't need to be necessarily an integer, right? It could be maybe n plus tau if you are in this, you know, weighted space or something. It's non-increasing. This is a so-called Bishop-Gromov property. So you can take the limit as r goes to infinity, and that's the minimum of this. And this is greater or equal than 0. And this we call asymptotic volume ratio. Well, it turned out that we can do business if this actually is not just greater or equal than 0, but strictly positive. So we assume from now on that our space satisfies this Euclidean volume growth property. So as an example, you should imagine that a cone, right, satisfies this property, but an infinite cylinder does not. Okay? So you need to have some kind of positive mass somewhere near infinity. So this is kind of the expectation. And so this is what we proved with Alexandru and Francesca, that we have such a CD0n space with an asymptotic volume growth which is strictly positive, because you see if this is 0, then we just have infinity here. It's a negative power. So actually you can think that the theorem is still true if this is 0, but then it's an empty statement, because on the right side you have infinity. But otherwise, you have really a constant here, which is this asymptotic volume growth. Okay, for the Euclidean space, that is 1, or, you know. And then you still have this kind of LSI. Moreover, this number here, this constant, is really sharp, in the sense that if you have a constant for which this is true, then this constant has to be necessarily greater than this number here. Okay. The proof is actually based not a direct proof which I presented to you, but it's based on an isoperimetric inequality which we proved earlier with Alexandru together. Namely, that if you have such a CD0n space with an asymptotic volume growth, right? Then you have really a Euclidean kind of isoperimetric inequality where the constant is replaced. So this is a Euclidean constant, but here you have this addition, this AVR constant here, which is a little bit smaller than this is always less or equal than 1, right? Which makes this inequality a little bit worse than the Euclidean one. But it is very similar in form as to the Euclidean isoperimetric inequality. Well, you should think again maybe on the cylinder, on the infinite cylinder. So if you take the infinite cylinder, this doesn't satisfy any isoperimetric inequality, right? Because here you have a volume which grows to infinity as you make the cylinder bigger and bigger, but here on the boundary it's a finite number, right? So you cannot bound the volume with some power of this finite number, right? So here you will have the perimeter, and here you would need to bound the measure of the cylinder, which is not possible. Of course, it's possible because the AVR there is 0, right? You should really think that this theorem works when this AVR is positive, like for the cone, for example, or for the Euclidean space, or, you know. Okay, so that was everything for kind of positively curved spaces. And this is the question we can ask. So what happens if your space doesn't have a lower curvature bound? So we thought with Alexandru to ask the best. So the Fields medalist should answer any question. So we asked Villani this question, and he said, no, this theory does not work unless you have a positive lower bound on the curvature. So, but still, maybe you want to prove, nevertheless, in spite of what Villani told us, so typical situation we are maybe concerned is this catenoid, right, where it is a minimal surface where it has a mean curvature 0, right? And the results do not apply because the Gauss curvature of this is negative. Okay, so what helps us is the so-called Michael-Simon inequality, which was invented by two Australian mathematicians, in a non-sharp form, and Simon Brandle in 2021 proved a sharp version of this. So I would like to recall the result of Brandle. It's an isoperimetric inequality which is for surfaces embedded in some higher dimensional Euclidean spaces, and then there the isoperimetric term, I mean this perimeter, is helped by the integral of the mean curvature. Okay, so you should think that if you have a minimal surface like a plane or a catenoid, here the mean curvature is 0, and you recover the kind of usual Euclidean isoperimetric inequality. But if it's not, then you still have something on the left where the kind of the mean curvature helps you. Well, this constant turns out to be sharp. I mean, m is the codimension here, right, of this manifold in Rn plus m. And it turns out that Brandle managed to prove the sharp constant for m equal to 1 and 2, which is exactly the Euclidean one. And for higher, m is still not known. So it's an open question whether such inequality with this constant replaced by the Euclidean constant is true or not. Okay? Even for minimal surfaces, it's not known. Okay, so his method was not with optimal transport. There is a competing method which is called the ABP method, Alexandru Beckham and Pucci. So I don't want to enter into this. You can read the papers of Brandle and Eichmeier. Especially, I can recommend you this very beautiful exposition in the notices of AMS 2 years ago. So that's the open question I mentioned before, whether the Michael-Simon inequality here holds in all codimensions with a sharp constant. The good news is that we know that the LSI actually holds in a sharp form for p equal to 2. So let me maybe... Okay, so this is some kind of repetition which you know from your, differential geometry or Riemannian geometry course. What is the second fundamental form is a kind of a way which shows you how the manifolds kind of sits in the ambient space, and you can express this as a second derivative, and the trace of this is actually the mean curvature vector. Is a vector. It's orthogonal, of course, if the codimension one is just a number, because it points into the normal direction. And now, what Simon Brendle proved in 2022 is that you have a similar form of the logarithmic Sobolev inequality as in the Euclidean case with the same constant, and here the mean curvature appears, an additional term. So if the mean curvature is 0, then this term does not appear. So you have really, like in the Euclidean case, the inequality. But he proved it for compact n-dimensional submanifolds without boundary. So immediately you can see the geometric content of this. That if h is 0, then you don't have any minimal submanifolds with no boundary, because you can take here a constant function, right, which makes this kind of minus infinity, right? This or very close to minus infinity. Anyway, it's a very small negative number, and you cannot bound that by this expression. Well, actually, minus infinity, right? Because the derivative of the constant function is actually 0, right? So that means that simply there are no minimal surfaces which are compact, which are embedded, right? But what about the other minimal surfaces? So this is the question we asked ourselves, and this is what we proved actually. The same thing without the restriction that the sigma is compact. Right? So we proved for all complete n-dimensional submanifolds embedded in Rn plus m that this inequality here holds. So for example, for the catenoid, the theorem of Brendle did not apply for the catenoid, for example. Okay. And moreover, we could characterize the equality cases, and namely equality holds if the submanifold is Rn, and f is the Gaussian, exactly as before. And the proof is by this method of OMT, which I presented in the beginning. So maybe I would like to indicate the modifications. So first of all, you look at the same starting measures, okay? But now the mu is a kind of not an absolutely continuous measure. It lives, it's a singular measure. It lives only on the sigma, all right? Just think about the catenoid. But the target measure is the Gaussian again, okay? So then you cannot apply the Brennier's theorem because that works only for absolutely continuous measures. So you cannot apply the Monge problem. But we have actually a Kantorovich relaxation of this problem, which I mentioned at the beginning of my talk. And this means that instead of looking at mappings, you look at measures which are defined on the product space here, which is sigma times Rn plus m, with the marginals here mu, and the other marginal should be nu, okay? And then you minimize this problem. So it turns out that if you do this, we recover a version of the Monge-Ampère equation. So kind of we liked so much this Brennier theorem that we developed our own version of this, and the own version is an integral version of the Brennier's theorem, which which means that you remember this Monge-Ampère equation. Here we have f squared on this, and here we have the determinant of some function times essentially this exponential. Now, this is more complicated because this phi it has a part which looks the same as before. It's a gradient of some good function, right? But it's actually defined on the normal bundle of sigma, right? And then you, of course, have an integral here. So how can we use this? Well, that's the equation, that the integral version of the Monge-Ampère equation. And well, still you can sort of estimate the determinant by the Laplacian, and then that's where the mean curvature also appears, mean curvature vector. But otherwise, actually, you can do more or less the same tricks as before by taking the logarithm, integrating by parts, but the additional term which appears is in terms of this mean curvature. Okay? But this is okay, because this is what you expect to have there. And then there is a modified version of this alpha, which is this number you need to plug in here when you optimize. And we get this kind of sharp form for p equal to 2. And actually, we can prove it for general p's. For minimal surfaces, we have this expression, which is for p equal to 2, you get back the previous one. And for non-minimal surfaces, it's a more complicated expression where also the mean curvature appears and a more complicated constant, which I didn't want to, write down. But it holds also. So if you are interested, you can see your papers in the Journal of AMS, which just appeared. So that was it. Sasha, happy birthday, and thank you for your attention.
I maybe forgot something, but so in Gaussian case, the right-hand side doesn't have any logarithm, right? It just
Yes, yeah, that's correct, yeah. And it's the Gaussian measure. Yeah, yeah. But actually, those versions are somehow easier to prove, to prove at least for non-sharp constants, and they hold also in the case of CDKN spaces in much greater generality due to this work of Lotte and Villani. In their ANAS papers, they prove such inequalities for Gaussian type or some probability measures, some reference measure, and okay, with non-sharp. I mean, in those spaces, you don't have an explicit constant there, but what we wanted to do is to get an inequality with a sharp constant and also characterize the equality cases. So this is where kind of our results kind of are better than the ones which were known before.
I'm speculating, but I would think that maybe there is a way to prove this inequality with Bernoulli.
Okay, we should talk about this. Yeah, yeah.
Okay, if not,
Thank you.
So our last speaker today is Professor Guillermo Rey from Madrid, and the title of his talk is Cancellated Sparse Domination.
Thank you very much. Thank you for the invitation. So this is joint work with Jose Conde Alonso and Emil Lorist, and it's a question that actually started back then in Michigan State University because I had a question about, oh, can you put the absolute value in another place? So this is where it started actually. But anyway, what am I talking about? So these are the main characters of my talk. They're singular integrals and variations of singular integrals. So I will start with the Hilbert transform, and it's basically convolution with 1 over x. And everything will be sort of like this, where I convolve with something that is not integral, but almost. Calderon-Simon operators are generalizations of this, where instead of 1 over x, I have something that is maybe not quite homogeneous, but almost acts as a convolution. I need some smoothness. If you like to think about the dyadic world or in the world of probability, then you can think of my singular integrals as Martingale transforms, or maybe SHA, as we will see later. And maybe the last character is the non-tangential maximal function. And maybe you can ask, what do I mean by non-tangential? Tangential to what? This is because this is coming from the harmonic extension to the upper half plane, and the non-tangential maximal function being bounded is related to the non-tangential behavior of the harmonic extension. So these are my characters. So what is known about this? This is a very, very, very classical topic from almost 100 years ago. We know that these people are bounded in LP for p between 1 and infinity, and bounded in the whole space. And this goes back to Ries and Calderon and Zygmunt and everyone. Then 40 years later, weighted LP estimates were proven, and they have been brought up today already. But I have I see them as a localization of these singular integrals. So these singular integrals, convolutions with 1 over x, they are not like the derivative. A derivative is a local property, right? If I evaluate the derivative here and I change it here, it doesn't change. But singular integrals are non-local. So weighted LP estimates are a way to sort of localize the action of a singular integral. And what do I mean by this? Well, imagine that I have a weight and I have a point, x naught, and I put most of the mass near x naught. If I have a weighted estimate like this, it means that if I change f far away from x naught, I should not change. I should not see a large change near x naught. This is why weighted estimate. Well, this is one way of saying weighted estimates are useful. They are a constraint of how much non-local an operator can be. So these were proven a long time ago. And then in the 2010s, sparse domination came up, and many people were involved. many people before me were involved. And I see it as a manifestation of something that I'm calling Stein's principle because I read somewhere, and I don't remember where, that this is due to Stein. But basically, the principle says that if you have a singular integral, the behavior is actually more or less mandated or something by the maximal function, by some maximal function. If anyone knows the true source of this, I am all ears, but I'm just going to call it Stein's principle because it's a safe bet. So exactly the behavior of a singular integral is determined by the corresponding maximal function. Well, what better manifestation than sparse domination? Because sparse domination, if I change this sum and I change it to a better operator, which is the supremum, then this is exactly saying that the maximal function is actually dominated by a maximal function, right? If this is a sup, then this is the maximal function. So it's not quite a maximal function. There is a sum, but the sum is over something that are called sparse sets. They have already shown up in Stephanie's talk. I will say more about this, but for now, imagine that sparse collections are basically almost disjoint. And if they were actually disjoint, then this would be a maximal function. All right. So all of these are conspicuously missing the endpoints. And they are missing the endpoints because the endpoints, I should have said, sorry. This notation has already shown up, but it's the average. I should say that this sparse domination implies all the others. So anyway, what about the extremes? In the extremes, the LP boundedness just fails. And it can fail in different ways, but the answer is different. So in L infinity, these integrals or singular integrals, except for the maximal function, they don't bound L infinity to L infinity. You have to map to a larger class. It's called VMO. And when p equals 1, L1 to L1 also fails, also for the maximal function. And there are two ways to fix it. You can either enlarge the landing space. Oops, sorry. You can enlarge the landing space, or you can restrict your source space. And the two questions have two different answers. So if you want to keep L1, then you have to go to weak L1 later. And if you want to end in L1, then the classical answer is called the Hardy space. I'm talking about the harmonic analysis Hardy space, but it's of course connected to the complex analytical one. So I will be talking mostly about this kind of direction. All right. So as I said, this is called the Hardy space. I have many friends in PDE, and for them H1 is something else. For me, it's those functions which have bounded maximal functions. Okay. This is, properly speaking, the dyadic Hardy space. If I want to talk about the normal Hardy space, then I should use generalized maximal functions. I'm not going to talk about that. Okay, so you can say, what do you mean, Guillet? I thought maximal functions are not bounded in L1. And many people have seen a theorem saying that a maximal function is in L1 if and only if the function is 0. So what am I talking about? Well, this is because the absolute value is inside the averages. If the absolute value is inside the averages, then this theorem is true, and then everything that I'm going to say doesn't have a content, because every inequality on the right-hand side will be in infinity. So the key point is that my maximal function, and that's why I called it the non-tangential maximal function, because that's where it matters. The absolute value is outside. And then this is not true if the absolute value is outside. If the absolute value is outside, the cancellation of f can play a role. And in fact, this is an example. Imagine that you have a function that is supported on a square and has mean 0. Okay? And let's say that we're only talking about the dyadic maximal function. If it's the dyadic maximal function, then every average over a larger square will be 0. So in fact, the maximal function will have compact support, which is already sort of killing the counterexample. And in this case, it's also bounded in L1 for different reasons. But anyway, so this is what I'm going to talk about. The maximal function has the absolute value outside. And I want to capture this subtlety of when is the maximal function in L1. Okay, I want to reach the hard space. Okay, so I'm going to talk about sparse domination, and this is the typical sparse domination, and you can see that the absolute values are inside. And if the absolute values are inside, this theory will never give you a H1 to L1 mapping, because it kills the cancellation. And if you put the absolute value inside, then you go back to my false theorem from before, where everything is infinity and nothing can work. But since I'm going to talk about sparse domination, I should say what is sparse. This, as I said, Stephanie has already introduced this, but I can do it again. So what do I mean by a sparse collection? I mean a collection of cubes. They don't have to be cubes. They can be any collection of elements, but let's say cubes. And every one of these cubes, it should be something that is almost disjoint. So one way to codify this is to say each of these cubes have hiding spots. And these hiding spots are actually pairwise disjoint. Okay, so imagine that you have a square, and I want this square to be able to hide from the others, or at least the others' hiding spots. So you can always hide, right? But you don't. The first condition says that your hiding spot cannot be too small, because otherwise it's very easy. You can just hide in the empty space, and well, hiding spots should be disjoint. So in this sequence of squares, this is a sparse collection, and the hiding spots are these colored parts, right? This is 3/4 of the square. This is 3/4 of this square. This is actually 100%. They are disjoint. This is a sparse collection. Okay, so this is what I would like, right? I said absolute values inside kill me, so I'm just going to put them outside. But this is false. This is not true. We can prove it we have actually a proof of this not being possible, right? I mean, one has to be careful with the quantifiers, but the theorem basically says there exist functions for which, if this were true, then a way to quantify how badly a collection is sparse goes to infinity. So you cannot have such a theorem. Okay, so what do we do? Maybe I'm going too fast. Okay, so I'm going to talk about a toy model. I promised to talk about singular integrals, and I will talk about them later. But first, let's start with maximal functions. So I want to, maybe these were not the first one to be shown to be sparsely dominated, but they were the easiest to be shown to be sparsely dominated. So maybe a toy model is, can you dominate with a sparse collection in some way the cancellative maximal function with cancellative things on the right-hand side? I just said that it's false. So obviously, as written, this is not going to work, but let's try anyway, because when I first thought about it, I actually thought it was true. So imagine you wanted to prove such a thing, and I'm going to give you an algorithm that will produce such a domination. It will fail, of course, but we will see. So what we're going to do is, I'm going to, first of all, my maximal function is going to be over a finite family of squares, okay? And it's it's so finite that I can sort all the squares by the average of f over these squares. Okay, and I'm going to take the cube over which the function has the largest average. And this is the cube. And with the first one, I just put it in my family. And a family with a single square is obviously sparse, because what better family than this, other than the empty family? So this is where I start, and then I go to the next cube. The next cube, by the next cube, I mean the cube which has the next largest average. Okay, and this cube can be in various places. Since everything is dyadic, it cannot be in many different places, but it can be outside of Q0. And if it's outside, it's disjoint. And since I want almost disjoint, then this doesn't actually hurt me. I'm going to put it in my family, okay? So if the next one is disjoint, I just put it in. If the next one is inside, then I'm going to discard it. Obviously, I don't want things to intersect, so it makes sense that I'm discarding this, but you should not feel too scared that I'm throwing away whatever, because the cube that I already put has a larger average, right? So if I don't put the purple one and I just keep the Q0, the maximal function with just Q0 is already larger than whatever the purple one would give me. So actually the purple doesn't give me any value. I can throw it away. And then this is the interesting case, right? What happens if it's not contained, it's not disjoint? The other possibility is that it contains it, right? And you can ask, okay, should I insert it? Should I not insert it? Okay, well, sparse collections have almost disjoint in a quantified way. And one way to quantify it is how much do you intersect the others, right? If you intersect too much, then you're not sparse. And if you intersect only a little, then it's okay. In this situation, you can quantify it, right? Okay, I'm going to say, well, I'm going to compute the union of all the previous cubes that I have inserted in my family. And I'm going to see how much that intersects with Q, relative to Q. And if it's not too much, okay, so if the intersection with the previous ones is not too much, I will insert it. And if it intersects too much, I'm going to throw it away. Now you should be scared about me throwing away too many things, but at least in this algorithm, I mean, you keep deciding whether to put it in or to put it out with all the finite number of cubes in your family. And at the end, by construction, you get a sparse collection. Because, I mean, maybe this is not so easy to see, especially with the definition that I used. But if every cube intersects only slightly the previous family, then you can define E of Q as Q without the previous ones. And this condition says that hiding spot is always large. Okay, so this does produce a sparse collection, and the key question is whether you have domination or not. Because I'm throwing away stuff, it is non-trivial that I'm saved. And in fact, this is not true, because I said it's not true, right? So what is true? Well, I need to give a name to the quantities that are appearing in this slide. And the way to, well, I forgot about this, but I just explained it with words. The way to quantify this is with something that's called medians, or maybe percentiles. So what is a median? The formulaic definition, I'm missing a closing brace, is the smallest height above which the function has a small level set. Okay, so maybe with a picture it's a little bit better. Suppose you have a cube Q and some function that is supported on Q or lives in Q in some way, and I choose a height. Okay, and I consider the level set of where the function is above this height. Okay, so the median is the smallest height such that the level set is less than 1/2. Okay, so it's the watermark. If you think about this as like some sort of topographic map, it's the watermark that says 50% of the mass, or splits 50% of the mass. So in the previous algorithm, I was discarding or keeping cubes based on this intersection, right? And in this way, then I can say, well, if I discard a cube, okay, it means that the intersection with all the previous ones was too large, or in other words, the median of the characteristic function of the previous ones is 1 in Q. Okay? And since all the previous ones, because of the order that I chose in this algorithm, the previous cubes have larger averages, right? That means that the median of the averages from before in this discarded cube is larger than the average of Q. So I can discard it. So this is saying Q was discarded, right? Because it intersects more than half of Q. And if this is true, then the median of the maximal function over this sparse collection has to be larger than the average of Q. So this maybe reckless throwing of cubes was not so reckless as soon as you enlarge your maximal function slightly. Okay? So this actually, you can put it in a theorem. You can say, well, okay, maybe I cannot prove such a pretty theorem for your typical maximal function, but if it's a maximal function over a finite number of cubes, which you can always assume by the monotone convergence theorem, then you have pointwise sparse domination with a sparse character on the right-hand side, but you have to pay with a median. And here I didn't write a subscript for this median, and if I don't write a subscript, I'm going to use something that we're calling the maximal median, for lack of a better word. I cannot use M because M is already taken, so we're calling it P for percentile. But it's the same definition as the maximal function. Instead of averages, you replace them with medians. Okay? So this theorem, I just gave you a proof, and I said it works. And I sort of used the dyadic nature of dyadic cubes, but that my usage was only for explanation. I actually did not use the fact that anything is dyadic. I didn't use the fact that anything is a cube. This is a theorem that works for measurable sets that are not zero, of course. If you have a maximal function over a collection of sets, they could be rectangles, they could be squares, they could be rotated shapes. It doesn't matter. You can always extract a subcollection of those sets, which is sparse, as long as you pay with this maximal median. Okay? So I was actually very happy because this gives, I like the multiparameter aspect of harmonic analysis, and this gives a sparse characterization of the multi-parameter Hardy space in terms of sparse collections. So the Hardy space norm of the function is equivalent to the definition is with the maximal function, but I can put a sparse maximal function over all sparse collections, or I can maybe add all of these averages. And one way to think about this expression is, okay, you cannot just take the L1 norm of your function with absolute values outside, but if I have a family of rectangles which is almost disjoint, and I put absolute values outside, then it is true that I can do this cancellative L1 norm. Okay. By the way, this maximal function, that it looks like I'm cheating, right? Because I'm proving such wonderful theorems that don't even have constants and are maybe even contradicting theorems that I have proved in the past. But this maximal median is actually not badly behaved. It is very well behaved. You have preservation of level sets, or not level sets, but preservation of the measures of level sets. So in particular, it's bounded on all LP spaces, at least for squares and for rectangles that are axis aligned. And with weights, this is also true. Okay, so I promised singular integrals. So this is one version of, or one instance of the theorems that we can prove. If you have a martingale transform, I'm going to talk about martingale transforms just because they live in the dyadic world, and that means that the cancellative maximal function is the one that I gave before. But if you have a martingale transform, then you can find a function, f. You can find a sparse collection of cubes. Now we are back to cubes, okay? Forget about rectangles for forever now. You can find a sparse collection of cubes such that the pointwise, the singular integral, whatever it is bounded by this sparse sum over cubes of these quantities. And part of the difficulty of this theorem was actually believing that this was useful, because we could prove this, but if I look at this, to me, this is a stupid theorem, because this is saying, not only do I have a maximal function on the right-hand side, I am summing over a sparse collection with maximal functions, and on top of that, I have a maximal median. What am I talking about? Well, actually, this is not bad. It recovers classical. I feel weird saying classical sparse domination because it's actually not so old, but maybe I'm old. It recovers the classical the classical sparse domination because the median of the maximal function is bounded by the average of the function with absolute values inside, and this is just a direct consequence of the weak type 1-1 of the maximal function. Right, the weak type 1-1 maximal function estimate says that the level set of the maximal function is bounded by 1 over lambda times. This is exactly what you need to prove a median estimate of something, right? So in fact, this theorem recovers or rather non-cancellative sparse domination, which is nice. Okay, so maybe this is not so stupid, but still, do you have what I wanted at the beginning, which is, can I map H1 to L1? Can I get the endpoint? Okay. I have already done a proof, so maybe I should not do this proof, but I promise it will be easy. So what I'm going to do is I'm going to take this right-hand side and I'm just going to integrate it. I want to say singular integrals map some space to L1. So what I have to do is I have to put an integral sign here, right, and see what I get. So let's see what you get. If I put an integral sign here, since the only non-constant element is the characteristic function, this is very easy, right? I just put the measure of the cube. And I'm going to organize these cubes into layers, okay? And this makes sense, right? I'm going to do the typical harmonic analysis thing of dyadic decomposition, but in this case, I'm dyadically decomposing the range into dyadic values, okay? So this is bounded by some 2 times 2 to the m, right? And I'm going to call Sm the cubes for which this is 2 to the m. So this is fine. Now I reorganized everything, and I notice that this is, if I just look at this is a sum of cubes over a sparse family. And I said before that sparse families are almost disjoint. If they were disjoint, then the sum of the measures is the measure of the union. In the sparse world, this is still true. A sparse collection satisfies that the sum of the areas of its elements is comparable to the measure of the union. This is called the Carlson condition. And you can bound this by the measure of the elements in Sm. So I will do that. And then Sm was a place where was the collection of cubes where the median of the maximal function is like 2 to the m. So in this union, I know that the maximal median of the maximal function is bounded below by 2 to the m. And now this is just the layer cake, the discrete layer cake representation of the integral. This is exactly the integral of the maximal median of the maximal function. And I just said before that this maximal median is very well behaved. It's bounded in L1. I can peel that off, and I get the maximal function. And this is what I wanted, right? Because that's the Hardy space. That's the Hardy norm, or the dyadic Hardy norm. So this proves H1 to L1, at least for the objects that I can put on the left-hand side, which are martingale transforms and square functions and things like this. What can I do with this? Well, I can prove cancellative weighted estimates. So in general, this sort of estimate is not true. Well, I'm missing a power p here and here, I'm sorry. So if I put absolute values, this is true, and this goes back to Koifman and Pfefferman. These sort of estimates go back to Koifman and Pfefferman, but with the non-cancellative maximum function. So if you want to put something that is smaller, the non-tangential or cancellative maximal function, then this is non-trivial. But you can prove it with this sparse domination, with this cancellative sparse domination. And this works for weights in any AP class, but you have to pay with a constant here that depends on p. So this is not, you cannot just remove the weight. I just mentioned that this gives a sparse characterization of H1, and I should stress that this is a sparse characterization of H1 outside of just dyadic squares. It can be multi-parameter setting, or it can be other settings. And this was part of the original motivation. I would like to prove cancellative or non-cancellative, whatever, sparse domination in the multi-parameter setting. And the typical proof of sparse domination always goes through a weak type 1-1 inequality of the involved operator. And that's not true in the multi-parameter setting. So I really like this proof because I didn't show you, but we don't use the weak type 1-1 of any operator. We use, well, I will show you what we use in a second, but we don't use the weak type 1-1, which would be false in this even one parameter setting. Okay. I'm sorry, I went way too fast. But what's the idea of the proof? Well, there are two important ideas. First of all, is this inequality that I'm just putting with in a very bare bones way. It says that the median of singular integral, be that the square function, the maximal function, a Calderon-Zygmunt operator, whatever, is bounded by the median of the maximal function. And in the spirit of Stein's principle, the maximal function on the right-hand side is the appropriate maximal function, okay? Not just whatever maximal function you like. So I actually really like this inequality. This is written in the probabilistic sense, but if you put Q and Q on both sides, then you get something that is true for Calderon-Zygmunt singular integrals, again with the appropriate definition of the maximal function. And I should say what happens in the continuous case. So when not in the martingale transform setting or the SHA operator, what do I mean by averaging? So it's no longer true that if I have like a compactly supported function with mean 0, that the appropriate maximal function, which is called the grand maximal function, is well behaved, because I need the function to have good cancellation properties with respect to smooth kernels, not just a standard characteristic function of a dyadic cube. So the way to get around this is this maximal function in the continuous case. It's the grand maximal function, right? It's the supremum over convolutions of f with smooth kernels. And the smoothness of the kernel can be almost as bad as I want, but it has to be a little bit smooth. And it's that a little bit smooth is capturing the kernel itself. So the grand maximal function here can involve the kernel itself of the operator that I'm trying to dominate. And since that is smooth, because I'm proving sparse domination for smooth Calderon-Stigman operators, then everything is fine. Okay, so I'm going to leave some open questions. So first of all, we used in the proof, in every step almost, except for the sparse characterization of H1, we use that the measure is doubling, and it's very interesting to ask if this can work in the non-doubling setting, and we of course thought about it, but there is a big obstacle because you would have to prove a different theorem. The theorem that I stated, if true, works for p larger than 0, and it is known, and this is an example that goes back to Marcinkiewicz and Zygmunt, that the square function does not map HP to LP for p less than 1. It's just not true in the non-doubling setting. In the probabilistic, they wrote it in the probabilistic world, so non-doubling for them means not regular, okay? But it's, for harmonic analysis, it's just non-doubling. So the theorem would have to change, because if you have sparse domination, at least as I wrote it, that implies estimates for all p. So something has to change when p is equal to 1 or less than 1. I would like to prove this for multi-parameter martingale transforms. This kills one leg of the enemy, which is the lack of weak type 1-1 sort of inequalities. So it gives some method, but there is another big obstacle, which is the localization of the operator. Or multi-parameter operators are very, or they are much less localized than normal martingale transforms. So part of the project is how do you delocalize these sort of things? We don't know. And then an interesting question is, in this estimate that I wrote here, if p is larger than 1, then you can put an A infinity there with something that doesn't depend on p. And here, with the cancellative one, we need some dependence like this, but it's unclear what is the sharp constant. So since we have many experts in sharp constants, maybe one of you can help me here. Okay, so maybe I will end here. And it's Vala. Thank you again, and happy birthday, Sasha.
Thank you. Other questions? Comments?
In connection with the non-doubling measures, I would, maybe correct me, but I would say that the sparse domination for p larger than 1 is not well understood, right?
It depends on on the operator that you want to sparsely dominate. So if it's SHA, definitely not. But if it's the martingale transforms, maybe something can be said.
No, but I mean Calderon-Stigman operators. Calderon-Stigman operators with non-doubling measures can be sparse domination work well in the non-doubling setting.
Right. But I'm talking about just martingale transforms. Right. Just martingale transforms. So I don't want this thing that Stephanie was doing this morning of subtracting siblings and just doing I'm just flipping signs on the martingale differences. And that is not outside the realm of possibilities. But very unclear exactly what happens, because it's just false for p less than 1. So probably something needs to be added to the right-hand side that is not integrable for p less than 1. Kind of, for those familiar, there is a paper by Davies called On the Integrability of the Square Function, where he gets things that are quantities that are only integrable for L1 or larger, but not for p less than 1. So maybe something like that can be done, but I'm not sure.
Other questions? Okay, if not, let's thank speaker again.
So let me just remind you that for those of you who signed up for the guided tour, we are